So Peter and Ivar, do you want me to open up the meeting, or you still want to wait for some people to come on?
No, I think you can get started.
Yeah, start.
Okay, sounds good. Okay, so good morning, everybody, and welcome to the workshop titled Searching for Axions in and with Quantum Materials. My name is Rob McQueenie. I'm a professor at Iowa State University. I'm a senior scientist at the Ames Laboratory, and I'm director of the Center for the Advancement of Topological Semimetals, or CATS, which is a DOE BES Energy Frontier Research Center, which is supporting this workshop. And so CATS has been around since 2018. We have a mission to discover and understand and harness new topological states of matter. And one of the focuses of the center has been on topological insulators and axions. And so over the last 6 or so years, the center's made a lot of seminal discoveries on the novel properties of axion or magnetic topological materials such as manganese, bismuth, tellurium. So for example, we've discovered electronic surface states. We've tried to understand how Chern insulators develop in metamagnetic states. We've discovered the layer Hall effect, the manipulation of antiferromagnetic domains with electric fields and light, axion circular dichroism, quantum metric nonlinear Hall effect, and on and on. And so a lot of these studies highlight the role of both electric and magnetic fields to manipulate transport and optical properties of axion insulators. And more recently, we've been expanding these studies to other magnetic topological insulators such as europium, indium-2, arsenic-2. And so, as I said, CATS, we periodically host topical workshops in focus areas of interest to the center. And so this particular workshop, or all the workshops we run, we hope they'll lead to new ideas and research directions through open dialogue, and hopefully new collaborations between CATS research and those of you in attendance, or maybe even the collaborators of those people. And so, I do want to thank Peter and Ivar for organizing the workshop. I want to thank all the speakers and attendees for spending time to attend the workshop and share their ideas. The agenda looks great. I'm really looking forward to learning a bit more about axions, and I'll turn it over, I guess, to Peter to chair the first session on axion quasiparticles in condensed matter.
Thank you, Rob. Yes, so also welcome everybody from me. So I'm Peter Ort. I was an associate professor at Iowa State until the beginning of this year. So I was part of CATS. I recently moved to Germany to a new position there at Saarland University, but I'm still collaborating with people and finishing up things. And so we had already started this planning for this workshop. So I'm very happy to feel like I'm back, even though it's virtual, with all the people from CATS. So yeah, so I mean, we have a nice agenda. Let me quickly show it for those. Let me see whether I'm able to show the right thing here. Yeah. So this is the agenda we have for today. So we have organized this into 2 sessions. The first one is more like a condensed matter session, and the second one is focused on fundamental axion search. So we always have an overview, an introductory speaker to kick off the session. In the condensed matter, that's Peter Armitage, and in the fundamental axion search, it's Catherine Zurek. She will be joining later. She said she's also at the West Coast, so she'll be joining a bit later. And then we have 3 speakers who are giving more details about this. So in the condensed matter section, we have Aikino Sekine, and I'm very grateful that you could make it, because I know it's very late for you already. So thanks a lot for staying up with us so long. So you'll be giving the first talk, and then Su Yang, who is in CATS, will give the second talk, and Pranaya Narang will give the third talk. And then we have the talk by Aaron Chu, who's already here from Fermilab, about searching for dark matter in the fundamental axion session. We have Dave Schuster from Stanford giving a talk there, and Sasha Balatsky giving a talk as well. And so we also leave plenty of time for an open discussion here after the lunch break in the condensed matter section, and at the end of the meeting for the fundamental axions or general. So this, we hope to that people engage in these discussions. Otherwise, Ivar and I will have some questions, but feel free to use this as an open venue for asking questions or having ideas or whatnot. I think at the end of the talks, we can also leave a couple of minutes for questions regarding the talks. So I leave this up to the speakers, but generally that's usually good. So if you finish a little bit early, a few minutes earlier, we can have some questions at the end of each talk. But if not, there will also be time during the discussion time. Okay, so without further waiting, let's start with the first talk. So let's see whether the sharing of the screen works and all that stuff. So Peter, if you want to.
Oh, and I guess one other thing, I think it's being recorded, right? And so if
people, I should say this.
People want to opt out of that, I think they can opt out of it. But
right. So so I think Ivar and Corey and I, we were thinking that maybe it would be nice to, for those who are okay with this, if we record the talks, then we can potentially just use them internally or post them publicly. So maybe if you tell us. You can tell us after the, first of all, you should tell us now if you don't want it to be recorded, and you can also send me an email later if you don't want it to be posted publicly, then we will just cut it out and use it internally. But yeah, only if you don't want it to be recorded and you don't, I don't know, say it and you realize later, you can also just send me an email, we'll delete it, that's also fine. So yeah, I think I'm say this now, but I know not everybody's here, so we'll ask before every talk. But so those who hear it have a bit of time to think about it. I mean, I leave this totally up to you, depending on what you show and so on. So maybe, then the first question would be for Peter, whether you would be okay if we record this, or you'd rather not have us record it.
No. I'm sure it's fine. Yeah, no, I expected it.
Okay, great. So then we'll do that.
I don't have any secrets.
That sounds great. I'm sure you have, but you may not tell us now. So, yeah, we're looking forward to your talk. So thanks a lot for agreeing to give the overview talk. I'm very much looking for your talk. Let's get started.
It's my pleasure. So thanks very much, Peter and Ivar and Rob for the invitation. So this is a very interesting topic for me. One that I've kind of been working on since it's, the history goes back a long ways, and that's in part what I'll talk about today. But since it's modern history, I've kind of been working on it since the beginning, and so I'm going to give a kind of a background to some of the ideas, the original ideas, and in particular in the context of how they appear in condensed matter physics. And so there's going to be lots of resonance with what happens in particle physics. One of the things that I want to do today also is kind of, I'm going to give you a kind of a bit of an unconventional take, perhaps, on some of these axion electrodynamics effects. My experience in reading through the literature is that this notion of axial electrodynamics has obviously captured the quote unquote public imagination. And my perspective in reading the literature is that there's very often some interpretation of experiments which kind of, let's say, at least on a number of occasions, have bordered on the fantastical. And I think that one of my goals in this overview is to kind of give, if you will, as I would like to say sometimes, kind of a balls and springs approach to what's happening in axion electrodynamics, and in this regard, kind of perhaps remove some of the mysticism that's regarding this field, because I think kind of a clear and alternative picture may lead to kind of more straightforward application of some experiments. So I don't want to get into there's some preliminaries that if I was talking to a less expert audience that I might talk about. This in particular is say a review of the concept of topological insulators. But let me just say that topological insulators are, in their ideal, in the absence, let's say, of bulk conductivity, are characterized as bulk insulating materials with topologically protected surface states. And although in many cases it's sufficient to characterize them as surface conductors, the perspective in axion electrodynamics is that it is better to characterize the material, the electromagnetic response of topological insulators, or with some particular considerations, better characterized as bulk magnetoelectrics. And so magnetoelectrics are materials where we apply a magnetic field and we get out an electric polarization, or we apply an electric field and we get out a magnetization. And indeed, to understand some aspects of topological insulators or topological materials, this perspective is essential. So where it's really much better to think of topological insulators or topological materials as bulk magnetoelectrics, and not kind of insulating 3D materials, but with metallic surfaces. Okay, so and I'll get to the various parts of this as we go. I've been fortunate to have funding from a few people on these topics over the years. The DOE historically, although in their wisdom, no longer. For a long time, I've been this research has been supported by the Gordon and Betty Moore Foundation, and we currently have a MURI, which is exactly devoted to this topic. I'm just going to flash through various people. I've been working on this for some time, and so just flash through various people that I've been fortunate to collaborate with for the DOE team, that the DOE funded team that was based at Johns Hopkins. We were interested in looking at intrinsic Axion insulators and finding high quality intrinsic Axion insulators. This is a topic that the Ames group and CATS is also interested in, and these are some of the people that are involved with it. The current MURI that we have ongoing, which is funded by the Army Research Office, has these people, kind of a dream team, if you will, for looking at these kinds of effects in solids. And for instance, my former student, Liang Wu, who's moved on to bigger and better things at Penn, Taylor Hughes, who wrote one of the early and seminal papers on this, my long-term collaborator, Shawn-Shik Oh, Kang Wang, Ki-Wook Kim, and Andrea Young are part of our MURI. Again, just kind of a historical perspective of some of the people that I've been fortunate to work with. My student, Liang Wu, almost all the work that I've done on this topic is with Shawn Oh, a variety of other people on topological semimetals, for which there's an Axion description of. My former student, Bing Cheng, who's actually currently as a postdoc at Ames, and current and former student Deepa John Chaudhuri, who's currently a postdoc at the University of Illinois. Okay, so I'm going to talk today about these kind of general considerations that go into finding and understanding this Axion magnetoelectric effect, or the topological magnetoelectric effect. And many of the ideas that I'm going to talk about today, if you're interested in some material on this, feel free to take a look at this kind of pedagogical paper or review that my former student Liang Wu and I wrote some years ago. Many of the ideas that I'll talk about can be found there. I'm going to do a number of things in this talk. I'm going to talk about a little bit about the history of Axion electrodynamics, how to get a kind of an intuitive understanding for what's happening in these materials. I'm going to make an extended analogy to the case of polarization in one dimension, which is an analogy that helped me at least understand a lot of what is actually happening in systems like this. And then we'll talk a little bit about the actual experiments we'll do. I'll give some perspective for the future. Okay, so background. So topological insulators. So of course, quantum Hall systems were the first topological insulators that we had. So we take a two-dimensional electron gas and we apply a strong magnetic field to it. This manifestly breaks time reversal symmetry, and there's there's going to be for the three-dimensional systems, there's a duality here, if you will, or two different perspectives on the way of looking at these systems. We can think about the two-dimensional conductance, if you will, that gives a quantized Hall response, or we can think about quantum Hall systems as two-dimensional insulators, which have going around them these one-way going edge states. And since the early days of quantum Hall, people asked if we can have systems that are like the quantum Hall, but let's say in 3 dimensions or in zero magnetic field. And the answer to both those questions is yes. And we, I think it wasn't clear for many years, but of course, with the advent of topological insulators and the realized significance of strong spin orbit coupling, that's clear how you can do that now, right? Where the spin orbit coupling plays the role in such systems of an effective magnetic field. And then we have materials that we might call two-dimensional topological insulators, also referred to as quantum spin Hall, and three-dimensional topological insulators. These are systems where, if you will, because the effect is coming from strong spin orbit coupling, then if you will, every electron in the system, it kind of carries with it its own fictitious magnetic field, which arises from this spin orbit coupling effect. So, of course, in the two-dimensional quantum Hall effect, we have quantum Hall plateaus, and if you apply a magnetic field to such systems and you measure the Hall resistance, the transverse resistance that goes as Planck's constant divided by E squared divided by an integer, and this quantization is exact to something like 1 part in 10 to the 9th. And, it was a early mystery, if you will, if each plateau has this exact quantity that they're characterized by, and every state there in the plateau has the same symmetry, not just all states there break time reversal symmetry manifestly because of the magnetic field applied. It was difficult to understand how each one of the states, if you will, each one of the quantum Hall plateau states could be different because the symmetries were the same. And trying to understand this is what led to the rise of topology, one of the aspects that led to the rise of topology in condensed matter physics, right? So now we understand that there's possible to find a quantity of the Berry curvature, and integrals over the Berry curvature in, let's say, a Brouin zone give rise to quantized quantities that you can relate to the Chern number and express the Hall conductance in this fashion. And this is one of the things that led to Thales getting the Nobel Prize. Okay, so so we can ask if topological insulators are materials like the quantum Hall systems, which have these quantized Hall resistances. Can we look for response functions in the topological insulators, which in principle have response functions which are quantized in the same way? And I think the answer early on was it wasn't clear. But in the spirit of the quantized Hall resistance and the quantum Hall effect, it was eventually realized that we can understand topological insulators as materials with a quantized magnetoelectric response. And so people like Sucheng Zhang and Joel Moore and David Vanderbilt worked this out very early on, as that we should regard topological insulators as magnetoelectrics, but with a quantized response, with some caveats that we'll talk about. And that's really the essence of what I'm discussing today. So what's a magnetoelectric? So magnetoelectrics first pointed out in the late 1950s by Jelshinsky that point group symmetries of certain materials allowed a mixed response, meaning that you can apply a magnetic field and get out an electrical polarization, or apply an electric field and get out a magnetization. The kinds of magnetoelectrics that were conceived of by Jelshinsky, these can be both spin or orbital responses. The most common magnetoelectric material is CR203, which is actually used as a pigment. If you have on your desk somewhere, if you have some piece of plastic which is green in it, it's very likely that the pigment in that plastic is actually CR203, which was the first magnetoelectric that was proposed by Jelshinsky. The magnetoelectric coefficients defined in the fashion that I give here on this slide are just a number that there's no particular significance to these alpha coefficients. It's characterized by this number that if you had a good enough theory that you might try to calculate. People like David Vanderbilt has had some success in doing this, but ultimately they're not special numbers. The magnetoelectric coefficient of chromium sesquioxide is a number like the resistance of copper at low temperatures. It's not a number with any particular significance. So CR203 is, in fact, it's also a mineral, and there's a kind of another image of that. In the case of CR203, it's a spin effect. And so CR203 has the corundum structure like sapphire, and it consists of hexagonal close pack array of these oxide anions, where, if you will, the octahedral holes in the structure are occupied by chromium. And when you apply an electric field to such a system, the magnetic ions move in such a way that if the electric field was zero, the net magnetization of the system would be zero. But if you apply an electric field to this kind of sublattice compensation isn't perfect anymore, and you get a net magnetization. And so that's a kind of a very general effect of how this kind of arise in the context of spin systems. And there's distinct symmetry considerations that allow this. There are other possibilities, and magnetoelectrics have appeared in different contexts before. So here's a proposal, for instance, from Chandra Varma, who believes that and has proposed that experiments in the cuprates are consistent with the pseudo-gap phase of the cuprates being due to bond orbital currents, essentially. And this orbital current state is proposed to have magnetoelectric effects. If you have states like this that were exhibited with bond currents kind of running around plaquettes in the copper oxygen planes and the cuprates, this would be a magnetoelectric. It has a very different symmetry considerations than that of chromium sesquioxide, but you can kind of see it in a kind of a similar cartoon fashion. If you apply an electric field, let's say in the diagonal direction to this plaquette, you kind of preferentially favor charge on a plus loop versus the minus loop, and you'll get an out of plane magnetization. And so the lesson from this is just that there are different possible contributions to magnetoelectric effects, and they have very different symmetries. In the case of CR203, then it is largely given by a magnetoelectric tensor, which is diagonal. But here, this is going to be off diagonal. You apply an electric field in the XY direction in plane, and you get a Z direction of magnetization. Okay, so what about in the context of topological insulators? Okay, so let's think of it for a second. Let's use the language of surface states for the topological insulator. And so let's imagine we have a slab of the topological insulator, which we understand to be everywhere ringed by this surface state. And it's a thought experiment, so I can do what I like here in this. And I'm going to, if you will, thread it by, I'm going to make everywhere a magnetic field, everywhere pointing out. You can imagine maybe threading it by a line of magnetic monopoles in some fashion like that. And that magnetic field that is everywhere threading out is going to be large enough to cause a quantum Hall effect in the surface. Okay, so if I have a quantum Hall effect in the surface, then this is going to result in a surface current. If I apply an electric field pointing up, let's call it the y direction, then this is going to give a surface current, which ends up circulating around this slab of topological insulator, if you will, let's say on the front surface in the x direction. So I have an electric field that is pushing on the charges, but they move in the x direction due to the quantum Hall effect, with a coefficient, the quantum Hall conductance, which is e squared over h times n plus 1/2. And we'll come back to this 1/2 in a moment, but let me just, for now, just say it's n plus 1/2. So a surface current can be rewritten as a bulk magnetization. And so surface current K can be written as a bulk magnetization, M cross N. And so the bulk magnetization in the Y direction is, a bulk magnetization in the Y direction comes from an electric field in the Y direction. And so that's a magnetization. And that's really the essence of the effect. This surface current is equivalent to a bulk magnetization. And so we've kind of come up with a very heuristic way of understanding how we can get a bulk magnetoelectric polarizability. So of course, in the original theory, it was done in a more sophisticated fashion. You can describe it by adding E dot B term to the conventional electromagnetic Lagrangian in the field theory language. This is the so-called axion term. Okay. One of the things that I want to point out in this is this E dot B term written here is this theta angle in front. Okay. I'll come back to this, but for an inversion symmetric system, this angle here, theta, which is this prefactor in front of the E squared over 2 pi h, this is constrained to be pi times an integer. Okay. And so, as I had mentioned, this exotic magnetoelectric effects, quantized axion electrodynamic responses, which we're going to talk about, things like induced monopoles. This was now proposed something 13 to 15 years ago by people like Sucheng Zhang and Joel Moore and David Vanderbilt and various junior collaborators of theirs. So the notion of axion electrodynamics had been postulated in 1977 in an attempt to explain the absence of charge parity violation in the strong interaction between quarks. So similar related ideas were proposed by Pache and Quinn, Weinberg and Wilczek. The name comes from Wilczek, and he called this particle the axion, because they, quote, cleaned up a problem with CP violation. And so we're going to hear some in the afternoon today, we're going to hear about some related ideas related to this. But as Wilczek has said, I called this particle the axion, after the laundry detergent, because that was a nice catchy name that sounded like a particle, and because this particular particle solved a problem involving axial currents. And in 1987, Wilczek had a paper, PRL, that pointed out that the existence of axions modifies the Maxwell's equations in this particular fashion here. So you have, for Gauss's law, you have a new source term that's proportional to the gradient of theta, again, this theta angle. And in the equation below, you have these terms as well that are proportional to the time derivatives of theta. And one of the things you can see, for instance, in the actual equations of motion, it's only derivatives of theta which appear, right? Time derivatives or spatial derivatives. And so that's going to give some context for one, why it is these terms are important at surfaces. That's where the gradient of theta is largest. And perhaps also give some insight on what we might hear about later today about dynamic axion effects, which where the time derivative of theta is important, right? So these are general expressions that can be applied to CR203 or the fundamental vacuum. But in the materials like topological insulators, extra considerations will apply, and I'll get to this in a moment. I just want to point out that in Wilczek's original paper, not original paper, this is the second paper in PRL in 87, entitled Two Applications of Axion Electrodynamics, he points out that this paper is mostly about the possibility of fundamental axions. But, and he says here, whether or not axions have any physical reality, their study can be a useful intellectual exercise. Goes on to say, also it is, as he argues, not beyond the realm of possibility that fields whose properties partially mimic those of axion fields can be realized in condensed matter systems. And then at the end goes on to say, is there a class of solids which realizes the Dirac equation with complex adjustable masses, of which earlier in the paper it explains how this is equivalent to the axion problem. Unfortunately, the mapping leads from a standard hopping Hamiltonian to effective Lagrangians like 9 is not very transparent, and I have not succeeded in finding examples, although I believe they exist. A relevant observation is that the complex mass terms violate P and T symmetry, and so they will arise only when one has non-trivial spin order in solids. And so there's a lot of insight in here. We don't necessarily need non-conventional, non-trivial spin order in solids, but Frank Wilczek, brilliant guy, but perhaps wasn't anticipating the qualitatively new effects that come in the context when one has spin orbit coupling. So when one has spin orbit coupling, then those kinds of hopping Hamiltonians that he was referring to have new functionality. So this idea of axion electrodynamics and the axion angle is quite generalizable. As I mentioned, if we have inversion symmetry, the axion angle theta is constrained to be an integer times pi. And then there's two possibilities. You have axion, you have theta times, you have theta is equal to pi times an even integer, an odd integer, which is say 0, 2, or 4, and that corresponds to the conventional vacuum around us, or it corresponds to an odd integer, pi, 3 pi, etc. And this is topological insulators, the example of topological insulators. Okay, and very often people have referred to the axion insulator system with magnetization on the top and bottom surfaces pointing opposite direction. That's the axion insulator, and I kind of disagree with this formulation. I think they're all axion insulators. It's just a matter if the axion angle winds from 0 to pi to say 2 pi. That would be the example of a three-dimensional topological insulator in magnetic field. Or if it goes from 0 to pi and then back to 0. And that's what is referred to sometimes as the 3D axion insulator. A 2D quantum anomalous Hall system, if it's a 2D, you can think of that as kind of a domain wall in the axion insulator theta angle, just jumping from 0 to 2 pi. And again, the gradient of this tells you something about the electromagnetic response. 3D magnetic vial systems can also have their responses discussed in the context of this language, where, but in that case, it's a continuously varying parameter theta inside the material, which you can imagine goes from say 0 to Q over D, where Q is the separation of the violence. Now, in this language, I've said a number of different things here, but for the experts, in this might have noticed kind of two things that I've said, which are a bit weird or counterintuitive, if you will, in with regards to what we conventionally understand for topological states of matter and what we understand for magnetoelectrics. So one thing that I said was that we could get this magnetoelectric response in topological insulators when the that was quantized when we have inversion symmetry in the system. And so we usually understand that in order to get a magnetoelectric, we have to break both inversion symmetry or time reversal symmetry. The other thing that I said was that the Hall response of the surface of a topological insulator would be E squared over H times N plus 1/2. And that 1/2 is unconventional because we know from Thouless and collaborators that all 2D insulators, in non-interacting insulators, have to have a Hall conductance, which is E squared over H times an integer. And that comes from these considerations of integrating the Berry curvature in the over the two-dimensional Brouin zone. So E squared over H times an integer, in a conventional system, that integer is just 0. But here there's a 1/2. And so there's two weird things in this above, and it turns out these two things are related. Let me just say a few things here kind of quickly in this, because I see that I'm a little bit running out of time, but I guess we'll have a little bit of time for discussion later on, and I started a few minutes late. So symmetry is important in understanding response functions, and so you can say, for instance, that it generally can impose null properties on various responses. And so we have two essential ideas here, I would say. One is what we will call Neumann's principle, is that the response function tensors are invariant under transformations that are contained in the point group of the material. Okay, so that again, the property tensors are constrained by symmetry. That seems perhaps obvious, but goes by the terminology of Neumann's principle. The other is that of the covariance principle that tells us that physical laws, for instance, response functions, are so-called covariant, that they're independent of a coordinate system that are used to describe them. And so for the case of magnetoelectrics, if we imagine that we have, for instance, a polarization that comes from a magnetic field, and we have, let's imagine we take inversion operation on this equation above. And the inversion operation tells if we invert the coordinate systems, then if we had a polarization, then we have to get minus that polarization. You kind of plug this through, and if a crystal has inversion symmetry, then you'll say that this magnetoelectric response tensor has to be 0, basically constrained by inversion symmetry to be 0. So, but what we'll find is that's actually not the case in topological insulators. And so here I want to give just a very a little bit of an analogy, if you will, to the analogy to polarization in one dimension, and I think it's an important one. And you may think I'm kind of belaboring a side point, but the analogy to topological systems will be immediately obvious afterwards. So there's a well-known problem in analogies in polarization, where I can imagine that if I have, let's say, take a 1D chain of positive and negative charges, and I want to compute the polarization of this system, that we're told perhaps in beginning textbooks that what I should do is identify some kind of microscopic dipole and get its dipole moment. And then from that, I can calculate, from this kind of general formula, I can calculate the bulk magnetization. The problem is, in a bulk material, what microscopic dipole do I choose? Do I choose this one, or do I choose this one? And the choice is not inconsequential, because I get completely opposite values for the polarization in either case. Not only that, I could imagine doing a symmetry transformation on the system, and for instance, if I stick and calculate the dipole from the original charges, I could even get a much larger polarization in this fashion, right? I can take a symmetry and just slide all the charges through this material, and moreover, you might know that or go from these kinds of symmetry considerations and understand that the conventional wisdom for how to calculate polarization in such systems is that inversion symmetric materials can't have polarization, but this conventional wisdom is wrong. And right, in this case, you can see that the bulk of this material has inversion, but none of the possible polarizations you could calculate are 0. Okay, and so this is a very direct analogy to what goes on in the context of topological materials. So what you find out here is that the formal bulk polarization has this ambiguity that, if you will, originates from the definition of the local dipole. But what turns out is that the polarization is actually a multi-valued quantity, right? Which we can only define up to modulo a charge, E/2 plus or minus NE, and this is N is an integer and it's quantized. And it's quantized as long as you have inversion symmetry. So the conventional wisdom is wrong that you don't have a you basically can't define a polarization in inversion symmetric material. There is the inversion symmetric material. This force has a polarization, and it's actually quantized, and it's quantized by symmetry. So there's another possibility. Let me just go through this here, and you can also imagine, for instance, taking these positive and negative charges and putting them right on top of each other in this fashion. And that's a structure which also has polarization. But all of the polarizations you would calculate here are not E/2 plus or minus NE, but is E plus or minus NE. And I'm running out of time, so let me just kind of jump through a little bit of the end here to this and just say this is exactly what happens in topological insulators, right? So a kind of a cartoon of a topological insulator is that you have E²/H Chern insulator layers, which are kind of sitting spatially on top of each other. And a version of a conventional insulator is just one where these are sitting right on top of each other. But in a topological insulator, they are displaced in this fashion from each other in such a way that leaves half E²/H hanging off into space. And that's your topological insulator surface state. And this can be also calculated to have a magnetoelectric response. There's a few kind of preliminary things I want to say. Let me just take 2 more minutes just to say that this was something that I got excited about some years ago, and I think probably these experiments are familiar to most people here. So let me just say there's a question about how to measure all of this, and we did it some number of years ago with time domain terahertz spectroscopy, where the particular considerations that I've told you about tell us that the Faraday rotation, as low frequency light passes through a system like this, will rotate with a Faraday rotation, but that rotation is quantized, and quantized in such a fashion such that in a low frequency limit, it should kind of sit along these dashed lines. You can do a number of things with this, and one of the things, for instance, we did with it was pull out a purely fine structure, a purely solid state measure, the fine structure constant, where the error was in the 4th decimal point. So there's a number of other things here, and it looks like I prepared a little bit too much. So I think I'm just going to kind of skip through the rest of this. And this it really needs to be understood not as a surface Hall response. It really is a bulk magnetoelectric response for reasons I'd be happy to tell you about. Maybe we can talk about that in the discussion system. And I think I'll just stop there and talk about these what I think are interesting topics for the futures. And this is one of the things that the CATS group is interested in, and that's looking at intrinsic axion insulators. I think we're still looking for what we need here is high quality materials, which I don't think there's a good material so far, which is really a very good bulk insulator, but has intrinsic magnetism and also these topological effects. I think dynamic axion effects, where you have this fluctuating theta angle, will also be interesting, and there's particular symmetry requirements that are necessary for those. And then this idea of axion response opens up the possibility that could be more, let's say, generalized into novel response functions. And so collaborator Taylor Hughes has a recent paper on magnetic quadrupole moments in the axion angle, where quadrupole moments kind of come out of a very similar treatment as that we've discussed in the context of this axion angle in the context of topological insulators. So I think I'll just stop there, and I don't know if there's any time for questions. Probably not much, but
Yeah.
hopefully that this has given you a kind of a good overview for what will happen in the rest of the mini conference today. So yeah, thanks for your attention.
Thank you very much. Yeah, no, I think we can, if there are questions, we can take a question or two. I mean, it's not. Yeah, thank you very much for this great talk. I mean, this gave a good overview. Oops, sorry, I have my own timer. All right, there was a question earlier. Somebody raised their hand. Yeah, sorry. Let me see how that works. Can you speak up, or do I need to unmute you? Let me see how that works here.
I think you can go.
Let me start with that. Yeah, okay, good.
Hi, Peter.
Go ahead, Anton.
Hi. Thanks a lot for a really nice talk. Can I understand? So you said you can think of topological insulator as these layers of quantum Hall. So can I understand it in the field theory language as, you have this theta term, theta, pi GADA, right? And that's basically a derivative of ADA.
Yep.
Is that the right?
Yeah, I think so. Yeah, I think it's kind of an equivalent way of doing it, right? So, I love the field theory formulation for these things, but I think sometimes it's also important to give you have complementary perspectives on this, and this is, if you will, a real space version of a topological insulator. The version of a conventional insulator, which is non-topological. This is exactly what the situation is in some transition metal dichalcogenides, right? Where you have a K and a K prime valley, and they're sitting on top of each other, but they each have E squared over H of opposite helicity. And so if you imagine, slabs of transition metal dichalcogenides where you have the K and the K prime valleys, this is exactly what a conventional insulator is. And so,
right, but I guess you're saying in topological insulator, they are separated spatially.
Yeah, then they're separated spatially. That's right. Yeah, in exactly the same way as you could think about, a chain of sodium chlorine atoms, and then asking what are the bound states at the end, which are half charges, which are E over 2.
Right.
Yeah, and so, this is a common, I don't need to tell you, this is a very common idea in condensed matter physics, where you get fractionalization, where you kind of lose you have some intrinsic unit. Let's imagine, a Haldane spin chain where you have spin ones, but you kind of lose the let's say when you average out in the bulk, you have 1 and -1 averaging to 0 in the bulk, but leaving 1/2s on the surfaces. And so it's a very similar thing that happens in in a sodium chlorine chain, which I've kind of made this cartoon of, but you could formalize that in Hamiltonian language, let's say in terms of the Su-Schrieffer-Heber model.
Right. Yep. No, I think this is a very nice picture. Yeah, I remember you told me about this a few years ago on a bus in Banff.
Yeah, that's right.
Back then, I
didn't
quite understand it back then, and only understood this.
Okay, well, that's because that's good, because I think that's only fair, because me trying to figure this stuff out was trying to understand your papers, written in a different language. So,
okay, thank you.
Yeah, Anand.
Anand, yeah, you can go next. Yeah.
I don't know if there are other questions.
Yeah, Ioannis Petridis had a question, but maybe Anand, do you want to go next? I think you can unmute yourself. I'm not sure I can. Anand, we cannot hear you. But
yeah, sorry, I was unable to mute because my microphone button was hidden here.
Sounds good.
So Peter, I have a very practical kind of question. So you mentioned that they have to be insulating in the bulk, but how insulating, right? And so if you imagine that I have a thin film of something that's not a great conductor, right?
Yeah.
And I'm measuring in the terahertz, right? So you can the skin depth being quite large, and you could perhaps accommodate electric field. So if I have if you will, stray carriers and such in the system, how badly does it interfere?
So what I would look at is this paper that we wrote some years ago. So I put some actual numbers there about how parasitic conductances affect these effects, right? So the example I gave is where I apply an electric field, and then I get a circulating current that gives me a magnetization. But there's another thought as well. Let's use the same language, that we're gonna turn on a magnetic field and then look for the polarization. And so then, how does a polarization develop in that language? Well, the time varying, as you turn on the magnetic field, that creates an electric field, due to the time varying magnetic field, which drives charge to the end of this block, which then gets polarized, and if you will, has to get stuck there, right? So that's how a DC polarization results, is the charge gets driven to the end of the end of the circuit.
It's an open circuit. It's an open circuit, right? So that's what I was thinking, that maybe
that's right. And so if you have any conductance, that allows the charge basically to leak back,
right,
if you will, right? So you could drive charge to the end of that slab, but then it's going to leak back into the bulk to kind of neutralize this. And so it's really a question about timescales, right? And so this is, it's going to be, so, you know, what's the beautiful experiment that you might do? The beautiful experiment you would do would be to get a perfect Axion insulator, apply an electric field to it, and measure this quantized magnetoelectric effect, you know, just by, or make a, you know, if you will, you know, evaporate leads onto this slab, this crystal, and make a capacitor, polarize the capacitor and make a magnetization, or apply a magnetic field and get out the electrical polarization. That would be the DC version of this, which would be a beautiful experiment to do, but I also think it's probably impossible because all the materials we have some parasitic conductances, which will allow, for instance, the polarization to leak back. So you can make, so it's about timescales. You got to be faster than the timescale where charge leaks. And if you make some estimates for this, lo and behold, it's, you know, lucky me, it's in the terahertz range. You need to be above that. But at the same time, you need to be below the scale where magnetic gaps exist in the system. So, you know, below the scale where the magnetic gap is, or Landau level spacings of the surfaces, but above the time scale that is basically set by the charge leakage rate. And that just turns out very often for the materials we've looked at is in the terahertz range, which is why these terahertz experiments were important.
Okay. Yeah. Thanks so much. Yeah.
This is discussed in this review and side post.
Oh,
this exact point. Yeah.
Thanks.
So we had one more question by Ioannis Petridis.
Hi. Thanks for the talk. I just wanted to clarify one thing. At some point, you showed that the axion angle can appear in different cases. You showed 4 cases there. But yeah, maybe you can go to the slide. Yeah, there. But in the 3rd case, this is a 2-dimensional material. How can an axion be defined in 2 dimensions? Because axions, I guess, from a band topology perspective, these are properties of 3-dimensional Brillouin zones. So in the 2-dimensional case, I don't see how an axion.
What I wanted to think about was the limit where you would say take a magnetic topological insulator slab and make it 2D. And the symmetry considerations of free space tell you that you know, so let me put it a different way. An axion angle winding by 2 pi corresponds to a Hall conductance of E²/h.
Yeah, but isn't it Hall conductance is related to the curvature, which is not the axion?
Is related to the curvature?
To the curvature, to Berry curvature, to you know, Chern number.
Yeah. So sorry. What's the exact question? So I want to think of the gradient of the axion angle as something proportional to the.
Yeah, it's just my confusion is that this is in 3 dimensions, what you're saying about the axion, but in 2 dimensions, the whole conductivity, even if it is anomalous, it will be some related to some Berry curvature and not an axion. I'm just trying to connect how you think about the axion appearing in 2 dimensions.
So I think that there probably is some, yeah. So if we take, you know, the particular formulation, let's say for a non-interacting topological insulator system in which we can, and I forget the particular form for how this is all calculated, starting from the Berry curvature in 3-dimensional topological insulator, and show how we can calculate theta from that in 3D, and then we take the 2D limit of that. That's probably a rather hard and perhaps impossible. There may be fundamental problems with this. I was more just kind of wanted you to think of the axion angle at a jump of 2 pi corresponds to a Hall conductance of E²/h. So,
but it wouldn't give the magnetization, right?
There's no magnetization in 2D. Yeah,
right?
Okay, maybe that's
and the polarization response of the axion.
That's right. It's a Hall conductance.
So it's a Hall conductivity, so it's related to curvature. It's just an analogy with.
So it's an analogy. That's if you will, right? So if you have 1/2 times E²/h from the top surface and 1/2 times E²/h from the bottom surface, and you bring these close to each other, 1/2 plus 1/2 is 1. And you know, I wasn't making a deeper point than that.
Okay, thank you.
Yep.
Thanks a lot. Yeah, so then maybe yeah, thanks a lot, Peter, for this great talk. I know you will.
It was interesting.
Hopefully...
Sorry to run over. I see we've just started and we're already 16 minutes late. So
well, that's fine. I mean, it usually happens, and we're also here for the discussion, and that's all good. All right. So we'll have more time to chat in the discussion later. And so let's maybe move on to the second talk by Akihiko Sekine from Fujitsu.
Yes.
Hello, nice to meet you. Let's see, can you share your screen?
Okay. Yeah.
Sounds
Can you
great.
see my screen?
Yeah.
I'm sorry.
So yeah, we can see it very well. So yeah, so you have half an hour, but if you leave a little bit of time for discussions, that's also great. I'm gonna remind you, I should say after 25 minutes, but yeah. So looking forward to your talk. Thank you very much for being here.
Okay. Thank you. First of all, I want to thank the organizers for inviting me to this workshop. And today, I'm going to talk about dynamical magnetic phenomena arising from axion field. Okay, this talk can be divided into two parts. The first part focuses on dynamical axion inserters, and these are about possible applications of topological materials in antiferromagnetic spintronics. And the second part focuses on static axion inserters, namely topological inserters. And this is about a possible application of topological inserters in quantum interconnect technology. Okay, let us consider three-dimensional insulators whose responses to external fields described by a logical term called the theta term. As Professor Armitage explained, in the ground state of such insulators, a linear magnetic relative effect occurs, and this coefficient theta takes 0 or pi modulo 2 pi in systems with time reverse symmetry or spatial inversion symmetry. Then it turns out that the value of theta can be arbitrary only when both time reversal and inversion symmetries are broken. Okay, in such systems, this theta can be even dependent on space and time, like this, when the system is excited by external forces. This dynamical part is called the dynamical axion field. And so far, several theoretical models have been proposed for the dynamical axion insulators. And basically, a dynamical axion field is identified as an antiferromagnetic spin wave excitation. So in this talk, I want to propose two emergent phenomena arising from the dynamical axion field. Okay, the first one is the dynamical chiral magnetic effect, which is AC current generation solely by magnetic fields in insulators. And the second one is the electric field induced antiferromagnetic resonance, which is an efficient generation of pure spin currents. Okay, let us start from this. And these works were done in collaboration with Professor Kentaro Nomura and Dr. Takahiro Chiba. Okay, for concreteness, let us consider the so-called Huckemeyer-Hubbard model on diamond lattice, which is an model for the dynamical axion insulator. In the mean field approximation, a antiferromagnetism occurs between the two sublattices, which breaks both time reversal and inversion symmetries. So in this antiferromagnetic insulator phase, a theta term is obtained, and the expression for theta is given as a function of the Néel field. So we can see that this antiferromagnetic spin wave excitation realizes a dynamical axion field like this. Okay, now let us think about what happens when a dynamical axion field is realized in insulators. Actually, an expression for the electric current is obtained, proposed by long time ago. And this current is generated by the spatial dependence and the time dependence of the Néel field. So this current induced by the electric field is an anomalous Hall effect because this current is perpendicular to the electric field, and the current induced by the magnetic field is called the so-called the chiral magnetic effect. So let us firstly consider this current. The chiral magnetic effect was originally proposed in particle theory, which indicates a DC current generation by a static magnetic field in the presence of a chemical potential difference between wire points. But as one can understood intuitively, this current does not exist in the ground state. So instead, I'd like to propose a dynamical realization of the chiral magnetic effect in insulators. Okay, to this end, we consider the dynamics of the staggered field antiferromagnetic to magnetic moment, which is described by a well-known equation. And by solving this equation, the antiferromagnetic resonance state, where all the spins are precessing uniformly, especially uniformly, is obtained like this. And by substituting this solution for the near field, we find that a AC current is generated by the antiferromagnetic resonance. Also, by substituting possible values, we find that this current takes an experimentally observable value. So because the antiferromagnetic magnetic resonance has two resonant frequencies, so the two peaks will be observed. Note that this current is generated solely by magnetic fields. Okay, next, let us briefly consider this anomalous Hall effect, which requires a spatial dependence of the near field. Okay, suppose that a one-dimensional antiferromagnetic spin texture or domain wall is present, which can be realized, for example, by attaching two ferromagnets with a relative angle. Then, as we have seen, this kind of spatial dependence gives rise to the anomalous Hall current. And by substituting possible values, we find that this anomalous Hall conductivity takes an observable value. Okay, next we consider the inverse effect of this dynamical quantum magnetic effect. The electrical control of magnets has been an important research theme in particular from the viewpoint of the practical application, such as in memories and hard disk drives. So far, a electric field induced ferromagnetic resonance has been experimentally realized, while the antiferromagnetic resonance is not yet realized. Okay, here I propose that this kind of electric field induced antiferromagnetic resonance can be realized in dynamical axion insulators. Again, for concreteness, we consider the Fouquet-Hubbard model and focuses this on this antiferromagnetic insulator phase. The free energy of a dynamical axion insulator is given by the trivial free energy and the contribution from the theta term. Here the point is that the coupling between the near field and a electric field through the theta term. So from this free energy, we can obtain the effective magnetic fields. And by solving the Landau-Lifshitz-Gilbert equation in the presence of a theta term, we can see that the antiferromagnetic resonance state driven by an AC electric field is realized. Here, this E dot B term, namely the theta term, acts as the driving force. So, which means that the resonance frequencies are not altered by the theta term. Okay, so let us think about how to detect this resonance state. So it is known that a DC pure spin current is generated from the near field, and this spin current flowing into the neighboring heavy metal contact is converted to a DC voltage via the inverse spin Hall effect. And assuming platinum contact with an AC electric field of 1 volt per meter, which is very small, we find that this DC voltage takes observable value. So in other words, the dynamical axion insulators can be an efficient generator of spin currents. Okay, finally, I want to briefly talk about microwave to light quantum transaction utilizing topological insulator heterostructures. Okay, the quantum transaction or quantum frequency conversion is an important technology that enables the interconnects between the quantum devices, such as quantum processors and quantum memories. It is also essential for the realization of scalable superconducting quantum computers. So with this direction in mind, we consider the quantum transaction between microwave and optical photons. Due to the large frequency difference between these photons, the conversion needs to be done via intermediate bosonic mode or nonlinear process. Here, the conversion efficiency is defined by the ratio between outgoing and incoming photon numbers. Okay, here we focus on the conversion via the magneto-optic effect, namely via magnon. So although the current conversion efficiency is low, the coupling between a superconducting qubit and a magnon has been experimentally realized, and also the operating temperature can be high compared to other methods. So we expect that there's room for improvement of this conversion method. So the previous studies using the ferromagnet YG have identified that the mass reduction efficiency is essentially determined by the right magnum interaction strength, which is proportional to the sample thickness. So this means that it is difficult to improve the mass reduction efficiency by changing this sample size inside the cavity. Here, I propose that the mass reduction efficiency can be greatly improved by utilizing topological insulated heterostructures consisting of a topological insulated thin film and a ferromagnetic insulated thin film. Okay, the mechanism is following as follows. So thanks to the topological Faraday effect, which is independent of the sample thickness, this mass reduction efficiency is inversely proportional to the thickness of the ferromagnetic insulated layer. This is in sharp contrast to the conventional ferromagnetic insulated case. And by substituting possible values, we find that the transaction efficiency can be improved about 6 orders of magnitude compared to the value obtained with a spherical ferromagnet YG. Okay, now the terahertz optical fibers are under active research and development. We expect that in the future, topological insulated heterostructures might be utilized as a quantum transducer for superconducting quantum computers into connected via terahertz optical fibers. Okay, this is the summary of my talk. And so, yeah, thank you very much for your attention.
Thank you very much. Wonderful. That was very interesting. Are there any questions?
I can ask a quick question. So one of the, I think one of the difficulties in this field is that we don't have good axion insulators, in the sense of, ones with an intrinsic
Yeah.
magnetism. We have to apply magnetic fields, and even then it's
Yeah,
only on specific materials. And so how affected are some of these things? So for instance, things like quantum transduction can be affected by bulk conduction effects.
Right.
I think this is in general a practical difficulty for this field in general. That was a question.
Sorry, I couldn't hear your question.
Mike, can everybody else hear me?
Yeah, we can hear you well. Yeah. Maybe just repeat the question. Maybe just didn't.
Oh, okay. No, the question was about for some of these things that you've talked about, how do issues like bulk conduction affect things? For instance, you talked about microwave to optical quantum transduction. We don't have a good intrinsic axion insulator, one that has its own magnetism. And so I wondered how, to what extent that's important.
So that's big important issue. So so basically we have to find a good material with a large bulk gap. So
So when you estimated these numbers, what material did you consider? When you had like some, right? In order to get, or did you consider a specific material in order to get this 10?
Okay, so 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 I have currently in mind a system like this one. So, but in these systems, the film level lies in the conduction band. So in order to get the good quantum transaction efficiency, so we have to move the film level to the inside the surface gap. So so the fine tuning will be necessary.
Thank you. Yeah, so assuming you probably won't stick around for the discussion because that's a bit late. If there is another urgent question, we can take it. Otherwise, we would move on. But if there's one more question, feel free to just speak up. Or Ivar, you had unmuted yourself. Did you have anything?
No, it was like a technical detail. It doesn't matter. It's fine.
Okay. All right. So in this case, thank you very much, for the nice talk and for staying up so long. And we'll move on with the next talk, which is given by Suyang Xu from Harvard about optical axion induction. Sorry. So Suyang, go ahead and share your screen if you. Yeah, so as I said before, we can see it. So is it okay if we record it or?
Yeah, of course.
Yeah. Okay, so you have 30 minutes, including questions. I can remind you after 25 in the chat, but I mean, we have plenty of time later also for discussion. Yeah, looking forward to your talk. Thanks for being here.
All right. So, good morning, everyone, or good evening for friends in Asia. But it's a great pleasure for me to share our recent work. So I'm going to talk about how we use light helicity to probe and to control antiferromagnetic order. And I'll also talk about how it's related to axion electrodynamics. So let me motivate a little bit more broadly. So we know that in chemistry and biology, controlling chirality and understanding homochirality in biology are greatly important problems. And one of the ways that chemists have been trying to use to control let's say, the outcome of a chemical reaction in a chiral-dependent way is to shine circularly polarized light. So what we have been doing is sort of analogous to this, because if we think about the left and right chirality are degenerate, then in an antiferromagnet we also have two degenerate states. So here I'm drawing a layered antiferromagnet, up down versus down up, right? So they're degenerate. So if I cool down across the Néel temperature, then they can both show up with the same probability. Then sort of in a random way if I cool down many times. So what we have shown in this work is that we can actually use light helicity to control which of the degenerate antiferromic state we obtain in a definitive way. And the mechanism is related to this axion magnetoelectric coupling. So let me motivate why we are interested in antiferromagnets. Well, compared to ferromagnets, antiferromagnets have zero net magnetic moment. And as a result, these antiferromagnetic state that I talked about can be quite robust against a external B field or a stray field. Also, antiferromagnets, they're essentially much faster compared to ferromagnets, and also just from the material science point of view, there are just naturally many more antiferromagnetic materials than ferromagnets. But going back to the robustness is kind of also a double-edged sword, because it's robust. On the other hand, it also means that the lack of a net magnetization, which is typically what we use for a ferromagnet to either detect a ferromagnet or to control the direction of the magnetization, would be absent in the antiferromagnet. So it's hard to detect and hard to control. And I'm going to talk about optical study in this sense. So and the technique that we use is really, really simple and very well established. But since not everyone is in this community, let me just briefly explain. So basically, it's called the circular dichroism. Essentially, think about I have a material, then I shine circularly polarized light. I can measure the transmission coefficient, and I can measure that for both sigma plus and sigma minus light. And their difference is essentially the circular dichroism, the difference of the transmission coefficient. And because I'm measuring that in transmission, I can also put a T in front, right? So this TCD, or transmission circular dichroism, is closely related to another important phenomena where I would use linearly polarized light and look at the rotation of the light polarization in the transmission, which is called the Faraday rotation. Now, if I could do that in transmission, then there's no reason I can't do that in reflection. If I measure the reflection coefficient difference between sigma plus and sigma minus light, then that's called RCD, or is closely related to so-called Kerr effect or Kerr rotation. And typically, these kind of effects are widely used in physics to study the net magnetization in an optical way. And there's a common perception that somehow these phenomena are linearly proportional to the net magnetization. And what I want to show you is that actually, even in fully compensated antiferromagnet where there's no global net magnetization, one can still have a circular dichroism, but it only happens in the reflection channel, but it's absent in the transmission channel. And that's also the foundation that we use in some sense, to control these antiferromagnetic order. So the material that I'm going to talk about is this manganese bismuth telluride, which is an intrinsic topological insulator, a magnetic topological insulator. If I look from the side view, there are every unit cell has 7 atomic layers arranged in this way. And this is a van der Waals material, so this unit cell repeats in Z direction, and they're separated by, they're identical and they're separated by van der Waals gaps. So later on, when I say monolayer, I don't mean a monoatomic layer, I mean a mono unit cell, right? One unit cell of manganese bismuth 2 tellurium 4. When I say bilayer, I mean 2 unit cells in that way. So if I cool down, these materials are intrinsically magnetically ordered. Within every layer, the manganese spins are ferromagnetically ordered with the spin in the Z direction, but the interlayer is antiferromagnetic coupled, right? So they're alternating. This was only synthesized quite recently, and people are quite excited about them. So ARP has showed these Dirac surface stages like the bismuth telluride, and another detail that I should mention is that this layered antiferromagnetic order is the ground state, but if I apply a really strong vertical magnetic field, external one, then I can force all the spin to be parallel to the B field that requires about 6 or 7 Tesla, then I reach the so-called ferromagnetic state. But the ground state without magnetic field is antiferromagnetic, just like I mentioned. Okay, so then basically, because it's van der Waals, we could mechanically exfoliate down to a few layer limit, just like graphene. And because it's layer antiferromagnet, then that means the net magnetization will depend on the evenness or oddness of the layer. And in turn, the topology actually also change even versus odd. Specifically, when I have an odd number of layers, the material is expected to be a quantized anomalous Hall effect. And then there's actually as you can see, obviously, it behaves a little bit like a ferromagnet here. It has a net magnetization, obvious one. But when I have even number of layers, supposed to be fully quantized, and it's supposed to be a axion insulator. So we are going to mostly focus on the even layer, but we'll use the odd layer as a compare and contrast, like what do people expect from a ferromagnet in that sense. And yeah, I should also say that, although I talk about the effect that I'm talking about is realized in this topological axion insulator, but these optical effects are actually general because they're not quantized. Then one could actually generalize that to other kind of antiferromagnets that have the same symmetry. I'll explain more. What do I mean here? So let me go to the data. So basically, as I said, we can mechanically exfoliate them. So here the numbers are basically the number of unit cells in the Z direction. So these are thin films. So we can see that here we have a flake that has 4 areas that have different number of unit cells or layers. Here is the data. This is in the reflection geometry. So I'm measuring the reflection circular dichroism. In other words, the difference of the reflection coefficient between sigma plus and sigma minus light. And the x-axis here is the magnetic field. Like I mentioned, the antiferromagnetic state occurs at 0 magnetic field. So let's focus near B equals to 0. And we can clearly see here that, the odd layers clearly have a large non-zero RCD at 0 magnetic field, whereas the even number of layers have essentially 0 signal. So, so what we observe here is consistent with the common perception that the circular dichroism or it's some sort of linearly measure of the net magnetization. But actually, then what I'm going to show you now is I'm gonna stay at 0 magnetic field, but this is at using a red laser, helium neon laser at 633 nanometer. So I'm gonna fix the magnetic field at 0 and measure this magnitude of the RCD as a function of the photon energy or the wavelengths that I use. So what you see here, first of all, is that this spectrum, there's a nice segregation. For the odd layers has an M shape, for the even layers has a different shape. But what is most important is that even for the even layers, which we would expect 0 signal, actually there is a pretty large signal that is on the similar orders of magnitude as the odd layers. But you may say, okay, why didn't you see that in the previous slide? Well, that's because we use the 633 nanometer, which unfortunately, or accidentally, is very close to the 0 crossing of this spectrum of the even layers, whereas for the odd layer, you can clearly see that it's non-zero. So then according to this spectrum, then a simple prediction we can make is if you choose a different photon energy like this 900 something, then it's actually very close to the 0 crossing of the odd layer, but it's not. It's actually the even layer will have a non-zero signal. So therefore, we performed that measurement as a function of magnetic field now using a 946 nanometer laser. So you can see that now, the even layers actually have a non-zero RCD at 0 magnetic field, whereas the odd layers has nothing. Okay, so therefore, I'm going back to this RCD as a function of wavelengths. So the key message that I want to say is that essentially, in the antiferromagnetic state, we observe non-zero reflection circular dichroism, not only for odd layers, which we can easily understand based on this, common wisdom or knowledge that, the circular dichroism is a measure of the net magnetization, and in the odd layers, I have a net magnetization, so therefore there's a proportionality, which is wavelength dependent, and that also depends on the electronic structure, this coefficient. But the same logic wouldn't actually work for even layers because suppose we have 0 net magnetization, so therefore it wouldn't work. So then we had this data a long time ago, and we were very confused, and we start to look at doing other experiments and also, check the literature. And what we found is actually this has been considered previously, and indeed, actually, for a fully compensated antiferromagnet, there could be a circular dichroism, but there is a quite a nice distinction with that of in a ferromagnet, which is in a ferromagnet, you would expect the circular dichroism both when you measure in reflection channel and in transmission channel, whereas if the sample is really fully compensated, then you only expect that in the antiferromagnet, in the reflection channel, but it's absent in the transmission channel. Okay. So it's like this. So therefore, really to see that if what we have observed in the even layers is from this so-called antiferromagnetic CD, then we should also do the transmission experiment, right? So that's basically what we did. And before showing the data, I should also say that actually in chromium oxide, another classical fully compensated antiferromagnetic material insulator, people have also observed this Kerr effect in the reflection channel, but there was no simultaneous reflection and transmission channel measurements to the best of our knowledge. So basically then we have these flakes in a transparent substrate, and the flake itself only absorbed a few % of the light, so we could easily do both reflection and transmission. So here I first put the laser spot on the 5 layer and show you both the reflection and transmission signal, and we see that they're very similar. Okay, so they both show a large circular dichroism. Now, if I move my laser spot to the 6th layer and do the same experiment, then strikingly, I only see CD in the reflection channel, but absent in the transmission channel. And this obviously is at a fixed photon energy or wavelength, but I could also measure the spectrum, right? So here in this, I'm showing you the transmission circular dichroism for 5 and 6 layers at 0 magnetic field. We can see that for the 5 layers, the transmission spectrum is similar to that of the reflection. It has an M shape, but for the even layers is 0 at every wavelength. So really, what we have observed is this new kind of, it is an interesting kind of antiferromagnetic circular dichroism, which is a measure of the antiferromagnetic order, but there's no net magnetization. And if we put it in a broader context, just look at the symmetry classification, there's actually a very interesting correspondence. When we have a ferromagnet, like I said, we expect the signal in both reflection and transmission. When we have these antiferromagnet, then it's only in the reflection. And then, in chemistry, we have these chiral molecule, which are non-magnetic, and we have this optical activity phenomena. And it turns out because of the time reversal symmetry, the circular dichroism or the optical rotation only happens in the transmission channel. So and then if you look at the symmetry, actually, these reflection CD is only a measure of the breaking of time reversal symmetry. So it could be either ferromagnetic or antiferromagnet. And to distinguish them, one has to also measure the transmission. Okay, so we have sort of realized or observed these optical measure of this fully compensated antiferromagnetic order. So then we thought that the fact that we observe a circular dichroism means that for the antiferromagnetic state, it absorbs left and right light differently. So if we think about the absorption in some sort of energy picture, that means that when the light couples with the antiferromagnetic order, it sort of makes the degenerate antiferromagnetic state non-degenerate. So in other words, we tilt to the free energy landscape. So that means that somehow there's a chance we can use light helicity to choose which antiferromagnetic state we form. So the idea is then we can always shine the light with a constant helicity as we cool across the Néel temperature. And depending on the light helicity, we'll end up with one antiferromagnetic state over the other. So experimentally, what we do is we have this even layered manganese bismuth telluride. We shine, this is CW continuous wave laser, not a strongly pulsed femtosecond laser, and we just always shine a fixed helicity as we cool down. Okay, and across the Néel temperature around 25 Kelvin, when we reach the base temperature, we turn off this training light or induction light, depends on how you call it. And then we need to know whether we have made the magic or not, whether we have chosen an antiferromagnetic domain or not. So the way that we distinguish is to use this circular dichroism that I just told you, which means that, again, we would turn on another light, but here the light will be oscillating helicity, and then we're using the lock-in technique to measure the difference of reflection between these two sigma plus and sigma minus light, and that detection light, so-called, it's a much weaker. Okay, because we don't want to perturb the antiferromagnetic state. We just only want to detect which state we have measured. So basically here is the data once after the optical induction, and then we measure the CD as we warm up again from base temperature to above TC, and we can see that indeed we reach opposite antiferromagnetic state depending on the training light helicity. And obviously we repeated this measurement many times to see that this is not a coincidence. And actually this induction, obviously we need to always warm up the entire sample above the TC and cool down with the light. We have also tried whether we can directly switch, meaning that we stay below the Néel temperature and just use a, now instead of a continuous wave light, induction light, we use a pulsed laser, a femtosecond laser, which supposedly has a much larger electric field at a given time point. So then we see that we can actually park at around 17 or 18 Kelvin, which is below 25, and we can prepare a single antiferromagnetic state and we just use the light to directly switch locally the antiferromagnetic order. There are many more studies of time resolve and other things that one can do, which this is still kind of preliminary. We found that this just works at this temperature. So let me spend the last few minutes to talk about how this phenomena is related to the axion electrodynamics. So essentially, we know that this axion electrodynamics leads to a topological magnetoelectric effect, and this theta angle, which is essentially the trace of this magnetoelectric coefficient, is quantized in the axion insulator. And when we talk about this topological phenomena and quantization, we inexplicitly we're thinking about a quasi DC measurement where the electric field or the magnetic field that we apply are either static or very slowly vary, right? Very, very slow. But there's no reason that we cannot really generalize this idea to much higher frequency. For instance, think about the electric field of the light, which is in terahertz, much higher than terahertz, maybe like hundreds of terahertz, right? So in that case, then I would be able to generate a polarization that is oscillating also at that frequency, and then I can define this magnetoelectric coefficient or the theta angle at that frequency, right? So it turns out that this kind of generalization to the optical frequency is quite non-trivial, and specifically the trace part of the magnetoelectric coefficient, which is the theta angle, has not really been generalized before to the optical frequency. In our working with Dr. Junyoung Ah and Professor Ashwin Vishwanath at Harvard, they realized that the phenomena that we observe, this antiferromagnetic CD, is basically related to this this axion angle at the optical frequency. Yeah, so basically in this theory paper, they actually managed to generalize this axial angle for a quasi two-dimensional system up to optical frequency, and then basically now we can compute these axion angle, but not the DC one, right, at optical frequency. And you can see that even for an axion insulator like MBT, these theta angle at optical frequency is not quantized at all, right? Because if I would go to lambda equals to infinity or omega equals to 0, then theta is very close to quantization. But at optical frequency, this is a wavelength dependent generic value. And that also explains why I say that we can use that also for trivial antiferromagnetic insulator, because this is not related to DC quantization phenomena. It's an optical property. Okay, but anyways, so using this generalized optical axion electrodynamics, we can compute these CD value, and theoretically, and it actually matches quite well with our experiment. Finally, let me just also give a sort of an intuitive picture why this magnetoelectric coefficient give rise to a CD only in the reflection, but not in the transmission. So this can be very easily thought from these. So suppose I have these even number of layers MBT, which, like I mentioned, is an axion insulator, so it's magnetoelectric. So although I did not really suppose this is not in vacuum, or just it's a how do you say freestanding, right? I did not really apply any intentional electric field, but still my top and bottom surfaces are essentially interface with vacuum, right? So then I can conceptually thought there is an effective surface electric field due to the interfacial effect, and these effective surface electric field are opposite for the top and bottom surfaces, right? So as a result, because the sample is magnetoelectric, that means that there is a spontaneous surface magnetization, right? Which is the magnetoelectric coefficient multiplies this effective surface electric field. And the surface magnetization, or effectively the surface Hall conductivity, reflectivity is also opposite for the opposite surfaces. Okay. Now, if I shine light and I have a detector, let's say in the transmission part, any photon that makes to my transmission detector, right? It has to go through. It can just go through top and bottom once. It can also bounce back and forth in my MBT layer many times, and eventually goes out in transmission. But it doesn't really matter. Every photon that reaches my transmission detector has to go through my top and bottom surfaces in the equal amount of times. Whereas every photon that reaches my reflection detector can sense the top layer more than the bottom layer. And this, although the surface magnetization that I talk about fully compensate each other, but the fact that I sense the top layer more than the bottom layer using the reflection method basically gives me this antiferromagnetic circular dichroism. So this is kind of a intuitive picture why this only happens in reflection but not in transmission. Okay, so lastly, let me just say, because this workshop is mostly about trying to search for condensed matter version of the axion particle or quasi-particle, I should say that we should not really. It's kind of confusing in the sense that what I talked about, this axion angle at the optical frequency, is different from the dynamical axion, because here I'm just saying that the axion angle arises from this static antiferromagnetic material, but I'm talking about the axion response not at DC but at a finite frequency. But this theta angle, is a property of the static antiferromagnetic material, so it's not really changing as a function of time. Whereas the dynamical axion is really to look for some I somehow excite the system so that the antiferromagnetic state or the antiferromagnetic spins start to oscillate in time, and as a result, the DC axion angle also start to oscillate in time. That would be very interesting, but it's different from what we have observed here. So finally, let me just say that, like I said, although we realize this in the MBT, which is topological, but there's no reason we can't do that in chromium triiodide even layers or in chromium oxide. There's a possibility to use light helicity to control the antiferromagnetic order there, and there's also some interesting connection to the pseudogap state or the loop current order that people are thinking in these cuprates, which I'm not an expert at all, but I found some interesting literatures there. And finally, we could also use two induction light and we can control their helicity independently, and they're spatially close to each other, and as a result we can actually realize antiferromagnetic domain walls. And in our material, which is topological, then there's a chance that there is a ballistic edge state that can be optically generated in this way. That's it. So let me just thank all the collaborators. So the work is done by Jianqiang Qiu, which is a student in our group. And the theory, like I said, was done by Dr. Junyong Ah and Professor Vishwanath. We got the MBT ball crystals from Professor Nini at UCLA. And I also like to thank all the funding agencies. Thank you very much.
Thank you very much, Suyang. This was great. Do we have any quick questions? Otherwise, we can also have more discussion in the discussion section. I don't want to move too long, but is there any questions you want to ask now?
I have a question now, but I could ask it also later in discussion.
Go ahead. I mean, go ahead. We had questions for all the other talks.
So so thanks for the talk. So one of the things that I wonder, about, and you kind of alluded to this, to what extent this axion language is necessary, not just possible but necessary, and I wonder at high frequencies in the optical range whether it's necessary. In the low frequencies, you kind of do need it, because the axion language to regard, and this is what I mentioned in my talk, is that we kind of have some in the semi-classical perspective. You have a notion that you can regard topological insulators as surface conductors or bulk magnetoelectrics, but it's impossible to get within with our usual understanding to get a half quantized Hall conductance from a 2D material. And the fact that you have half quantized conductance really shows that you need to understand the surface states of topological insulators or their electrodynamic response as coming not from a 2D material, but from the boundary of a 3D material. And that's really because of this half quantized Hall effect. You can't get otherwise. And so I wonder to what extent Axion electrodynamic perspective at optical frequencies is not just possible but necessary. I don't know if you have a comment on that.
Yes, and I think Junyong is here, so if what I said is a little bit incorrect, please feel free to correct me. But I think this can be seen from, actually, this was one of the papers that tries to generalize this concept of magnetoelectric effect to the optical frequency by Ivo Souza and his collaborator. Basically, if we think about any magnetoelectric material, and if we think about this material as a homogeneous media, 3D translational invariant without any boundary, then actually, and one can calculate this kind of spatially dispersive optical conductivity. And through that, it turns out that one can only get the traceless part of the magnetoelectric coefficient, even at optical frequency. In order to see the trace part of the alpha, even at optical frequency, we need to specify the surface. In other words, these alpha, this trace part of the optical magnetoelectric coefficient is also a property of the surface, but it's somehow related to the bulk. The correspondence is not as strong as that in the DC limit, where because there in the DC limit, as you said, the Hall conductance on the surface is quantized. So as a result, the axion angle is also quantized in the bulk. In the optical frequency, essentially the trace part of the alpha is also a measure of the Hall conductivity of the surface, but at the optical frequency, which is non-quantized. But we do need the surface in order to see what is the trace part of alpha, essentially. So without the surface, it's kind of ill-defined. So in that sense, we can say that there is some, we can call it axion or not. I mean, the language is really, it doesn't really matter how we call it. But so I think there's some, it's not as good as the DC in the sense that it's not quantized, but there is a connection because we really need to know the surface in order to know the trace part. If we just imagine a translational invariant material without the surface, then this cannot really be, this effect will not be there, essentially. Yeah.
Okay. Yeah, the other issue that comes up in this, and I have to go run to teach, but I'll be back later. The other issue that comes up in this, I mean, I guess it's kind of a related issue, but a little bit different than what I was getting at, is to what extent, because we always have a constitutive relation between E and B in a material that we need to kind of regard effects as magnetoelectric versus magnetic or electric. But yeah, but I agree that the surface, and there's a lot of ambiguity in this. These issues that you kind of alluded to about whether you get rotation and reflection from a commensurate antiferromagnet. I think the confusion arose in large part because people don't really even now understand how to set the boundary conditions from a very basic perspective. There's symmetry arguments that tell you an effect should be finite or not, but the boundary conditions are, I think, still a little bit, I don't know of a good explanation of them. There's this factor of 1/2 that's kind of coming around that I don't think was ever motivated, but is you need that in order to get the right result. Anyway, we can discuss more perhaps in the
Happy to.
discussion section. Yeah, thanks.
Sounds great. Yeah, let's continue that discussion in the discussion section. So we have one more talk before our break, and then we'll continue with the discussion. Awesome.
And I'm
right,
bummed Peter will miss it, but
I'll tune in. It's being recorded, so I'll have to see it afterwards. I promise.
That's good.
Yeah, sorry about that. We were like, I mean, I guess we were. We should have like had
giving
40
him a
minutes.
hard time.
Yeah. So sounds good. So yeah, so the next talk is given by Professor Narang from UCLA, and about Axion electrodynamics through the lens of condensed matter. Yeah, we're happy that you are here and looking forward to your talk. Please go ahead.
Awesome. All right. So thank you so much for having me here. And I'm really excited to talk about this work that is going on in the group. And, we've heard wonderful talks about work that sits at this boundary of axion electrodynamics motivated from high energy, but seen now through condensed matter. And I want to point out that in my talk, but also in the field generally, and perhaps this will get reconciled also with the talks in the afternoon, there are two related but distinct concepts. One where we think about the axion quasi-particle in condensed matter, another where we're thinking about using types of excitations in condensed matter for detection schemes. And both of these involve some of the same types of excitations and quasi-particles that are near and dear to my heart, including some of the work that's happening in valence heavy metals, and of course in polaritons. And so I just want you to keep that in mind as we're going through this talk, that some of the language will mathematically translate over, but also some concepts really are across both of those fields. I typically tend to run over, so I'll start with the acknowledgements and say that the work I'm going to present today, particularly the protocol that I'll spend some time talking about, is work done by Olivia Liebman and Dr. Yanis Petridis and Dr. John Curtis. They're on the call here. Some of the ideas going forward, been developing together with Dr. Emily Bean. She's here as well. And some of the earlier work we've done in thinking about the non-reciprocity associated with the axion electrodynamics is done by Tina Garcia. Very recently, we've been learning from Professor Catherine Zurich. I'll hear from her this afternoon, but particularly her very talented postdocs, Yikun and Kim, who spent a little bit of time explaining the other half of this, using condensed matter for direct detection schemes to us. The crystals and the samples we're getting are from our dear friend Claudia Felser. So I'll direct all questions about how big a crystal and what crystal quality to Claudia. So when we think about the axions, and of course, going back to something that has already been introduced, these really are there for us to think about the strong CP problem, the Pecha-Quinn mechanism in particular, hopefully reconciling the known physics and things that, of course, don't have an easy explanation. So it is a leading dark matter candidate. And as it was explained to me recently, it has become very fashionable, but I guess has gone through spans of being more and less fashionable. But for us in condensed matter, it really shows up as an emergent excitation and modifies electrodynamics associated with some of the topological condensed matter systems, which is what the past few talks have been discussing. So as a condensed matter person, and I'm used to thinking about order parameters, thinking about how we would map everything in life onto one of these Mexican hat type potentials. So here we can just think of the axion being a collective excitation associated with the fields. And we're thinking of a pseudoscalar and something with zero spin. So mathematically, the effects of action associated with axion electrodynamics, which has been introduced so far, it shows up with this angle. And we heard talk from so young. It's something that we ought to be able to also relate to microscopic properties in condensed matter. So if you're thinking about the band structure, you're thinking about some other microscopic observable, this really ought to be directly mapped onto it. And the signatures here showing up as a topological magnetoelectric response, as Peter very nicely introduced some minutes ago. So now, when we take this apart and we take apart the electromagnetic Lagrangian here, I want to draw your attention to the equation of motion. The equation of motion here associated with the axion. This is the same nonlinear magnetoelectric coupling as we'll hear about this afternoon. But there are various components to it. So we think about the kinetic energy term, dispersion, and then the magnetoelectric coupling. And our contribution to the current here comes from two components, really, the chiral magnetic fields and the anomalous Hall. So within this, and this is something that we wrote about and reviewed in 2020, of course, really just captured what was happening and had happened up until that point. It was that the axion term would give us these unusual magnetoelectric transport terms, and that really it has been the predominant way that the folks have gone about characterizing it. So I don't want to dwell on this. This has already been discussed, but there is a nice connection, as always, there is in topology, to thinking about topological insulator physics. So now, as we start to think about the dynamical axion in topological insulators, we're really interested in introducing something that has antiferromagnetic order to TIs. And MBT, a material that was just talked about, has been thought about in this context. Really, microscopically, what we're talking about is have these magnetic fluctuations of a TI that then couple to the axion field, and that's what promotes it to becoming a dynamical field delta theta. So our approach to it, and what I'm going to spend some time on over the next several minutes, is to think about axions in Wahl semimetals, and not just because I absolutely love Wahl semimetals, but primarily because it turns out Wahl semimetals naturally have an axion term that is related to kind of the separation of the nodes in K-space. And in fact, thinking about the static versus the dynamic axion here can then just be associated with talking about these nodes being separated versus if a CW or spin density wave essentially gaps these out, right? So Wahl nodes act as magnetic monopoles. We know that you need these, they come in pairs with handedness, and they need to come together to mutually annihilate, and then of course need to be with opposite chirality. So it's all well and good. I think plenty has been thought about and written about in Wahl semimetals, including their optical response, which is good because part of the claim here is going to be that we want to, via optics in Wahl semimetals, say something about the axion field. So those of you who are about to zone out, please don't, because that's what we're building up towards. Wrong direction. So we naturally see the static axion here. That's what's characterized by the separation of the nodes. And very, very naively, without making any claims about how many pairs of nodes we have, compensated, uncompensated, tilted, not tilted, really, really simply, I can just take the separation of the nodes and use that to parameterize this data term. And there's a fair bit where I can go with just that, right? And our first foray into this was to say, with the separation of the nodes, thinking about Wahl semimetals, maybe I could just talk about non-reciprocity in Wahl semimetals. And here, the axion electrodynamics would contribute to something that shows up in the asymmetry of epsilon, or even of, well, certainly in chi, but also in chi2 and other nonlinear responses. Okay, but I'm getting ahead of myself because first I need to tell you how we go from the static axion to a dynamic axion, introduce a protocol that was really from Olivia, and then kind of get to that non-reciprocity component. So when we turn on interactions, and it turns out turning on interactions in the context of a valid semi-metal is essentially launching a CDW. We know a lot about CDW physics and how it essentially links the valid nodes, but really it gaps them out, and it promotes our axion now to being a dynamical field. So now we think of the axion as being a collective mode of this dynamical phase, and we are of course now talking about the order parameter here being associated with the CDW. So why we've gone about doing that is because then now the dynamical axion in these types of systems gains its own dynamics, which is good because now I can write out that same equation of motion of the axion, and in that context talk about there being a driven damped harmonic oscillator, and the force term there would then be proportional to this GE dot B term, right? So nice order parameter. We're all, at least in condensed matter, familiar with this, and really in the context of what we use for theta is the static part, just the separation of nodes, and then there's dynamical part, which we're now talking about essentially, if you wanted to visualize this, as a sliding motion relative to the lattice associated with that CDW. So all of that was background to now say that we want to be able to detect this. And unlike some of the talks we've heard so far, I'm going to call this a protocol that is all optical, and say a few things about how you would realize this protocol, but also leave some things general here, because perhaps you want to do this in the near IR, mid IR, or in the terahertz, as Peter alluded to, but maybe there are other spectral bands where some of these measurements would be easier. Okay, so this detection protocol, and just kind of to remind you, we're now going to focus on the axion component in valid semi-metals. We're not, this could all be applied to MBT type systems, and I promise I didn't plan this with the talk given by Su Young, but that coupling to that nonlinear coupling to the EM field certainly would show up even in the types of measurements I'm proposing here. But the one I want you to keep in mind is the one associated with the valid semi-metal. Okay, so there are going to be two components to this, and all of it is really going to be around this axion equation of motion. So first step is going to be for us to actually excite this mode, and this is a little bit tricky, but let me walk you through it. So first, we're exciting this nonlinearly through a 2-photon scheme, okay? And it not only is a 2-photon scheme where the 2 photons are random, but there is a distinct dependence that is related to the incident angle here. And we're also going to end up using the polarization associated with these, because that's something that's going to show up in the detection scheme. So now the axion is minimally excited by these two fields, and this should all look very familiar from very standard optics. Nothing too crazy happening here, but there are lots of things that we needed to show. Particularly introduce this phenomenological damping parameter, make sure this whole thing survives, make sure that we can actually excite the axion mode. So yes, we can. And now we're writing delta theta in terms of omega-1, omega-2, the frequencies associated with this 2-photon excitation and the momenta. And the appearance of this essentially triple product here is going to constrain the amplitude of the axion mode that we can get. But in order for this essentially to be non-zero, the claim is that the two polarizations that we have, right? So remember, we'll start out with this 2-photon excitation. These need to be non-collinear, and also non-collinear relative to the 4 momenta that we have. And our response will depend on, of course, the frequency of excitation. Remember, I said we could think about this in the near mid IR terahertz, but maybe there are things that are outside my imagination. And then there is, of course, the angle of the incident beams that'll show up. So with all of that, let's just look at what the axion amplitude looks like versus the frequencies. So I can think about, so let's just go back and make sure we're all talking about, so this is theta here, this is phi, and we're talking about the two beams that are coming in here, okay? So that's what that A1 and A2 is, and we're tracking the polarizations, okay? Okay, so all good so far. So for a phi that's 0, phi that's pi over 4, or a phi that's pi over 2, we can essentially think about with a set of beam frequencies, kind of just sweep through them for that 2-photon measurement, what kind of axion amplitude you'd expect to see. So there are some details here that I'm going to, I don't want to say sweep under the rug, but I guess that is effectively what I'm going to do here. So talk about a 2-photon, just a direct absorption term, have two active channels where you get kind of a Raman-like response, or get a stimulated Raman type response. And for those of you who come from optics, this is relatively straightforward. But for those of you who are thinking, what's really going on? Basically, I'm trying to establish that there is some meaningful information from that excitation angle and absorption that isn't just pumping in more energy into the system without keeping that information, okay? So with that, this second step is now detecting this, so fine. You've started out with a crazy 2-photon excitation, controlling all these things, but what are we really detecting? And the claim is that in goes something that's linearly polarized, out comes something that is elliptically polarized. Can't get simpler than that. And I don't need anything ultra fancy to see this. All I need are a set of Fresnel equations, do some field matching, and tell you what the reflection and absorption here would be, and then what you would actually detect out in this elliptically polarized sense, right? So let's just say there's something we can do here where we get an axion resonant frequency, which then allows us to estimate the size of the effect, right? This is another way of saying that I need to incorporate here something associated with the specific material system, the specific where I'm actually measuring this, and that kind of goes into this G delta theta. I'll just estimate this is 1.2. This is kind of the one parameter that is a moving parameter in our theory, which is fine because so far I've told you everything about this protocol, but stayed quite agnostic to the material in which this would actually happen. So long story short, the optical signature here is that the reflected light, you go in with something linearly polarized, you'll come out with something that's elliptically polarized. This ought to show up in a Kerr rotation measurement, and the Kerr rotation angle here is going to oscillate exactly in phase with the axion oscillations in the system. And we can see this both with sweeping through the excitations and then just directly linking that back to the Kerr angle that ought to be detectable. So the claim here was that, we have this ability to do very, very precise Kerr rotation measurements. And here we would end up doing essentially a time resolved Kerr rotation because we have the two pump type excitation going in here. So that was essentially our protocol, and I want to point you to the reference from Olivia and Giannis to take a look at that. But building on that, and I've kind of done this essentially in the order of first introducing the protocol and then talking about the types of systems under consideration, because I think some of the magnetic ballast systems that we're really interested in, particularly for non-reciprocity, are candidates for this detection scheme, are candidates for this optical excitation detection scheme, but they're not the only ones. So I don't want our imagination for what this protocol could do, or what types of systems we could look at to be limited by the magnetic ball systems that we're going to consider for non-reciprocity. So the ones we're going to consider for non-reciprocity, remember we said with this dynamical axion, you end up with, well, first with the static, you have that separation between the nodes, and then dynamical is the one that's oscillating. Magnetic belts, semimetals in particular, are quite exciting because now that asymmetry in the dielectric tensor really ought to just show up even in a steady state type measurement. So the systems I'm interested in looking at are cobaltine sulfide, europium cadmium arsenide. There's a whole family of these European-based compounds, but also cobalt, manganese, gallium, and certain other half Voislers, which of course we can get in large quantities from Claudia. Their crystal structures look as so, and for those of you who are interested, we can actually calculate these. We can also do type binding on these. There's all manner of and level of complexity with the microscopics that we could bring to the table here. What's important is that we're interested in linking the response of these back to, well, first understanding how the magnetic ball component here would show up in the asymmetry of the dielectric tensor, the non-reciprocity, and then linking it back to that axion field. So just remember, we are either interested in breaking time reversal, inversion symmetry. This is something that is relatively straightforward, but the part that is a little bit of a jump is linking that broken symmetry now to electromagnetic non-reciprocity. For those of you this is not working knowledge, we think about emissivity and absorptivity as pairs. So essentially, Kirchhoff's law of radiation tells us that if we're at equilibrium, thermal equilibrium in particular, the emissivity and absorptivity ought to be equal for a given frequency, direction, and polarization of radiation. This is something that makes it really hard to do different kinds of thermal schemes, and something that folks have been trying to work with for quite some time. However, this assumes Lorentz reciprocity, which of course is going to be violated here. And long story short, you can think all of this as being related to the ability to break time reversal symmetry in magnetic valves. Okay, so what we realized is that, fine, we are breaking time reversal symmetry without implied fields for some of these magnetic valve semimetals. And this ought to mean that emissivity and absorptivity are not the same. And that difference now is going to be characterizing the degree of asymmetry in the permittivity tensor. We ought to be able to link back to this axion term. So that's really the claim. This is, for those of you thinking, why this seems like a insanely complicated measurement. Yes, but this violation of Kirchhoff's law actually is a field onto itself, and is quite exciting in its own right, particularly to make interesting kinds of waveguides where this back propagation will not be possible, ideally fully suppressed, but even if mostly suppressed, could be used in interesting optical schemes. So those of you trying to make devices, there's a whole reason to do it. Okay. So now we have a giant optical non-reciprocity. It's going to show up without an external B field. It's really important. We have the four classes of materials that I showed you. Here we're breaking time reversal, and that axion term is essentially directly responsible for the asymmetry in the permittivity tensor. And it's all going to go back to thinking about this theta here with the separation of the nodes, but you could also think about this in more complicated ways, linking it back to the anomalous Hall. I guess everything in topology really does come back to anomalous Hall. So this axionic origin, again, we remember our equation of motion. We've seen this a few times with a nonlinear drive term. The the axion current contributions, which we'd split up way back when into the anomalous Hall response. We kind of said, okay, well, there are two components, and I just glossed over it. Here, it's the first part of that response that is going to be responsible for our non-reciprocity. So phrased a different way, I would claim that the axion compactly represents the HA here. So we've shown this, and we've actually shown that you could, in a very conventional optics sense, talk about this non-reciprocity. It would show up as thermal non-reciprocity, but for the valence semi-metals that we're interested in, this is relatively easy to see. I'm not going to try and convince you in the next, I don't know, 30 seconds or whatever I have left, that we are not violating the second law, but you can go look at some of the papers and see that for yourselves. But now kind of getting back to the first claim I made, that polaritons in some of these systems are actually relevant, not just to see the axion quasi-particle, but also for us to think about direct detection schemes. So using various types of polaritons, photon polaritons, phagonon polaritons, and other kinds of dressed optical excitations has been motivated and really pioneering work by Catherine Zurich in that domain. But valence semi-metals, particularly the types that we just talked about, also have some of these interesting surface polaritons. And the claim is that we ought to be able to, in a scenario where, say, we're making some kind of grading, maybe we have some other way of patterning into these magnetic files, ought to be able to excite the polariton. The polariton would directly couple, and that ought to not only give you the non-reciprocity, but also become a probe for these systems. So we've done this so far in cobalt tin sulfide. There are experiments that have very, very recently completed and looking at the low temperature thermal non-reciprocity in the system. We think we've established that quite comprehensively. I don't want to show some of those results here today, particularly because the experiment is unpublished, but feel free to write me and I can tell you in more detail. But just to say that not just CSS, but even the cobalt, manganese, gallium, and the europium cadmium-based compounds have this effect that we are seeing experimentally. So it's not just it's not just all theory. With that, let me just wrap up. Oh yeah, the references here on the right, I didn't have those on some of the other slides. But I think there is a nice interplay between magnetic files, thinking about the optical response of valence semi-metals, both linear and nonlinear, and the work happening in axion electrodynamics. And I'd argue that this is a nice point for us to both search for, as the workshop claims, search for, but also search in axionic materials. So once again, acknowledge folks and thank you for being here. Happy to take questions.
Thank you very much. Thanks a lot. This was a great talk. We also have sufficient time because we were starting already at the end of the session anyway. So yeah, are there any questions? Otherwise, I have a quick question. So, I mean, could you maybe give me a bit more intuition about what is the frequency kind of behavior of this? I mean, at some slide there was saying we set the axion to resonance, just right, normalizing. So I mean, how, let's say in europium cadmium to arsenic 2, or in some that material I know a little bit. So how would I figure out, is this also a magnon then, or how should I think of this?
So you would think of it as let's just take europium cadmium arsenide as a concrete example. You pick out a pair of nodes where you can parameterize this as the separation between the nodes, and then that would be the excitation you'd go after. What we have shown is that if I do the full kind of calculation for the dielectric tensor, this effect doesn't go away just because the other bands are contributing or canceling it out. It will be about that pair of nodes, but you're not actually exciting directly a magnon in the system. There's a separate idea associated with, magnons that we could excite. You could even think about, it doesn't just have to be a magnon, it could be one of these Damon-Eschbach type modes that are of interest in other contexts. But we haven't established that yet. Here, it's much, much simpler. It's just that by having this ability to break time reversal, you have an asymmetry in the tensor, and that's something that's going to directly relate to theta. You could, the polariton associated with the magnetic fields is primarily to actually be able to couple in. It's not necessarily to be able to, use it the same way that folks have talked about phonon polaritons out of the system.
Okay.
Not so far, at least.
Thanks. Any other questions? Yeah, Ivar, go ahead.
I agree. Yeah, very nice talk. So I guess in the context of non-reciprocity, so you mentioned that there was at least potentially like an appearance of breaking second law. So could you elaborate on that?
Say that one more time. Breaking. There was a keyword I missed there.
So I thought that you mentioned that it may look like the second law of thermodynamics could have been broken. So could you elaborate?
Yeah, we're not okay. Yeah, so I get this question about this Kirchhoff's law thing kind of all the time. So we're not violating the second law. I just want to point out that when you talk about the emissivity and absorptivity not being pairs, there's just a specific part of the spectral band where that'll be true, but it's not going to be a broadband response in the sense that there'll be another part of the spectral band where, say, if you suppressed absorptivity, there'll be an enhanced emissivity. A separate part of the spectral band, the reverse will be true. Does that make sense?
Yeah, I guess so. So is it somehow related to the story with the circulators where?
Yes.
So is it?
Yeah. So okay, here I think somewhere I had this Kirchhoff's law component. So the reason people have been interested in violating this, and you perhaps have seen some talks by Chanwei Fan or Eli Yablanovich, is that folks want to reach this Landsberg limit. And turns out that one of the best ways to do it is to violate Kirchhoff's law. And what they have shown, this is not our work, is that Kirchhoff's law is not a requirement for thermodynamics. Is just a response that is related to the Lorentz reciprocity. So that means if I find a way to violate Lorentz reciprocity, which I can by breaking time reversal, I'm good to go. I don't have to reconcile anything additional. The hard part so far has been to find systems where this non-reciprocity shows up intrinsically, let's say, without applying a giant field, because the instant you're applying a giant field, using it in these tiny waveguides or other contexts becomes slightly impractical. So that's the context in which kind of folks have been thinking about it. And then once you have this, right? So once I have an epsilon with this off-diagonal term, life is good. I can do all kinds of photonics with it without worrying about it. There's a whole machinery associated with that. Hopefully I got a question there, Ivar.
Great. Are there any other questions? Yeah. We can also continue, hopefully, in the discussion. I don't know whether you're able to join.
I also see a good representation from our crew here, so they chime in with any additional thoughts.
Yeah, please do so.
Or not.
And also feel free to join
the early o'clock for theorists, you know.
I know. All right, so then maybe let's take a break, and I guess the plan was, and there's still the plan to reconvene at, okay, so now I'm going to say it's going to be 12:30 Central. So it's in exactly 1 hour, right? I think.
Yeah.
Good. So thanks. Okay, so we're gonna record these talks again. Maybe Ivar, you wanna give a little, question about whether people want that or not, and I'll leave it to you now. Yeah, thanks a lot. And
yeah, thank you very much, Peter, for sharing. And yeah, so Peter did sort of the lion's share of organizing, and as you saw, like sending emails. So we should really thank Peter for wonderful organization before he retires to sleep.
I'm still around, but thanks. Yeah, I'm happy to do that.
Yeah. So I'm sure the talks are going to be sufficiently exciting that he's going to stay up. So my name is Ivo Martin. I'm a physicist at Argonne National Lab, and I'm going to be chairing the second half of our mini workshop. So the first part was devoted to, mainly as you saw, to condensed matter realizations of axions. The second part is going to be sort of focused more on the fundamental axions, but still sort of with the idea that some of the material issues, some of the sort of exciting materials that were discussed previously may turn out to be helpful in this endeavor. And then hopefully, yeah, so towards the end, during the discussion, we can pull all these sort of strands together and see if there is sort of interesting, heretofore unthought of connection between the two subfields that we can identify. But even if not, I'm sure we'll have fun. So we are fortunate to have Catherine Zurich to give us an overview talk on using collective excitations for dark matter detection. So yeah, without further ado, please, Catherine, all yours.
Okay, thanks for the invitation to speak with you all. So I'm going to give quite a bit different emphasis, I think, either than the talks before or after, in the sense that I'm not going to actually focus on the axion. I'll have some discussion on the cases in which materials can be good as axion detectors, but I want to kind of zoom out and give a bird's eye view of what it is that we're looking for in target materials when we're searching for dark matter. So this is the bird's eye view. The range of masses that are consistent with the formation of structure in the universe is huge. It goes down to about 10 to the minus 22 eV, which corresponds to the de Broglie wavelength of scales that are a little bit shorter than the size of the Milky Way. And it can go all the way up to 1,000 solar mass. And if you convert that into particle physics units, the solar mass is about 10 to the 57 GeV. So there's a huge dynamic range. And so you have to organize your search for dark matter around detection techniques that are theoretically motivated. And the issue is that gravity is the weakest force by far. And so all the information that we have about dark matter is very coarse-grained. So I show this picture sometimes that we have the standard model sector, we have all this information, very rich information about materials and the structure within the standard model sector from, the structure of the standard model, and then you can build that on up. And currently we have this question mark over what's in the dark matter sector. And in order to gain more information, we have these peaks, which you can think of as being barriers that tell us about the strength of the interaction between what the visible sector and the dark sector. And so all the information that we have is from this highest peak, the weakest interactions, gravity, which works because, all the information is very coarse-grained. It's not on the individual particle level. But what we really rely on to see it in any kind of material at all, even axions, which have very weak couplings, have to have much stronger couplings than gravitational to be able to detect them in the laboratory, much stronger than gravitational. And so that's what we're up against. So you've got to use something as a guide to try to narrow this down. And I think the best motivated one to use as a guide is that if you're going to look for dark matter in a laboratory experiment, the best motivated way of looking for it is the same interactions that set the observed abundance in the universe should be the same interactions that fix the interaction rate in your material, in your target material. So particle physicists have been looking for dark matter, not through kind of collective modes, but through just scattering off of individual nuclei. And you can fix the dark matter standard model or nucleus interaction by fixing dark matter's abundance by this annihilation process in the early universe. So you observe some abundance of dark matter, and that allows one to fix this annihilation cross-section, which numerically, if you solve this equation, tells you that the interaction rate to annihilate to the standard model actually gives you a very precise number, 3 times 10 to the minus 26 centimeter cubed. It has some logarithmic dependence on the dark matter mass, but it's not very, very strong. And so when you work that out with the back of the envelope, you do an estimate of the interaction cross-section. And so you can just estimate that it goes like some coupling constant to the 4th power. There has to be some reduced mass between the dark matter and whatever target standard model state it's interacting with. And then there's the mediator. And it turns out that the natural mass scale to get that 3 times 10 to the minus 26 centimeter cubed per second is about 1 TeV, if you just work it out. And so that has been the motivator for looking for massive dark matter in this range right around 1 TeV. And so that's what direct detection experiments have been going after, is dark matter that interacts with the standard model, actually not via the Z boson. So this is going to be a plot that I'm going to show, is the dark matter nucleon cross-section as a function of the dark matter mass, zooming in again on this weak scale. And I should say that if dark matter interacts with the standard model by a single Z boson exchange, it actually gives rise to a really big scattering cross-section, about 10 to the minus 39 centimeters squared. So these solid lines, so where we're currently at right now is xenon 1 ton. We're now on N ton results. LZ is getting results as well down at this 10 to the minus 46 centimeters squared level. So we're already actually many orders of magnitude below kind of nominal weak interaction cross sections. And the region where we're probing right now through scattering off of nuclei, individual nuclei, is down in this window where you would be scattering off of the Higgs boson. So that's really been the push of the fundamental physics community, has been on this dark matter candidate. And I think there's a good reason for it, because you're fixing the relic abundance and the interaction with the standard model through the same interaction process, which is actually via known forces, the weak force, okay? So everything that I'm going to say after this actually goes beyond this paradigm, because the interaction with the standard model is going to have to come through a particle which is not within the standard model, okay? But we're still going to stick with this principle that the interaction that sets the abundance is also going to be driving the expected rate in whatever material you're interested in probing the dark matter. And in fact, for the case where the dark matter abundance is set through this annihilation process, you can see that there's a natural mass window to probe after the WIMP. And that is that if you just look at this formula, the annihilation cross-section goes like this coupling constant, and then there's a mass scale. Now, the weak coupling constant is a number which is not much smaller than 1. And theoretically, you cannot push these coupling constants up above about 4 pi. So that's telling you, if you just look at the scale of this, that pushing the mass scale up to the higher end and have that interaction fix the relic abundance and the interaction with the standard model is not very well motivated, simply because the rates are never going to be large enough for very heavy dark matter. But what is motivated is to start probing to lower masses. You can just push down this coupling constant and simultaneously push down the mass scale and still fix the relic abundance through the interaction with the standard model. Okay, so the question then becomes, how are we going to look for lighter dark matter particles? And of course, if you push it to even lighter dark matter particles below the electron volt scale, that's where you get into axion physics. And so there's been a lot of activity thinking about what kinds of systems would make this possible. So it happened to be the case that weak scale dark matter has about the same mass as target nuclei. A xenon nucleus has, 100 GeV mass. Dark matter at the weak scale has a mass around the same scale. And so therefore, when you work out the kinematics, it turns out that that's a really good kinematic matching process to have dark matter come in and just elastically recoil off of a single free nucleus. And as long as the energy deposition is much bigger than the typical phonon energy, I can treat that nucleus as being free. So this is the reason why the fundamental physics community working on dark matter detection until about 10 years ago really didn't have to think about condensed matter physics at all, because the relevant degrees of freedom were not, kind of material coherent degrees of freedom. You could just treat the excitation, which was just nuclear recoil, as being a free nucleus that was interacting with just this elastic scattering process. But as soon as the dark matter gets much lighter than 100 GeV, once it drops below about 10 GeV or even a little bit lower, then you have to start to think about collective excitations. One, because once the energy deposition drops below this 100 millieV approximate scale, the nucleus isn't free. And secondly, when the dark matter mass drops below the target nucleus mass, you can just look at this formula and realize that the energy deposition is going to be suppressed by a ratio of the dark matter mass to the target nucleus mass, which means that you're only extracting a very small fraction of the dark matter kinetic energy when it interacts. So if you want to look for dark matter below the weak scale, there are three main requirements. You've got to have some viable theoretical targets, which is what I've been talking about. Something that's motivated from a theory of dark matter. You've got to have a good interaction between your target material and the dark matter, which is a combination of the kinematic matching plus the interaction type. And this goes into the ideas for detection. And then you need to have sensitivity to sufficiently small energy deposits with low dark count rates. And really, this is the experimental and the technological requirements. So the rest of this talk is going to be divided into looking at those three things. So let's start talking briefly about the first one. You guys are all motivated about the axion, which is why I'm broadening this out and also talking about scattering processes. So instead of having dark matter annihilate to the standard model, I can have it freeze in. So this is a process where standard model particles annihilate to dark matter particles with a very small probability. They kind of leak into the dark matter. And that predicts an interaction cross-section. Now I want you to notice the mass scale here starts at 1 GeV and goes down. So this is the sub-WIMP scale. And then on the other hand, there's a model of dark matter that's called asymmetric dark matter, and that gives some other set of predictions. The point that I want to make here is that you have these predictions and the types of experiments that I'm going to talk about, or ideas for detection. All of these sensitivity curves are for a kilogram of target material that's exposed to the dark matter wind for a year, which is background free. Okay. So these are not very big detectors. They're relatively small detectors, and they can reach these models of dark matter. So before I go on, can I ask if there are any questions? No questions probably means you're not interested, but I'll keep going.
I had a question, but I forget what it was now. I didn't want to interrupt. I'll remember it and ask later. Thanks.
So I already said that nuclear recoil has been the standard, gold standard. It's can ignore materials physics because the energy depositions are large enough that you can approximate it just as a free recoil. As the energy deposition drops for lighter dark matter candidates, then what you have is dark matter that's not recoiling against individual particles, but what you really have to compute is the transition from your target, whatever it is, from an initial to a final state. So you can think about this as dark matter just deposits some momentum and energy onto the target, and then I need to do the quantum mechanical computation subject to all the dark matter physics. Okay, the dark matter physics is sitting in here in this form factor, and then you can parameterize, at least for spin-independent interactions, the response of the material in terms of this dynamic structure factor. So you should just think of this as dark matter is providing some momentum and energy, and what you want to do is look for a material with a strong response in the relevant kinematic regime. And then you want to compute that transition process. For spin-independent, it's pretty easy because you can just look up the dynamic structure factors. If there are other types of interactions, you have to compute the lattice potential and then compute how the lattice potential that the dark matter creates, and then compute how the lattice responds to whatever type of dark matter interaction there is. So this is an example of a lattice potential for a particular type of dark matter interaction, and then you need to compute these expectation values on the lattice. Okay, but the important thing that I want you to take away from this is that for many materials, you can just encapsulate, and dark matter interactions, you can just encapsulate the relevant information in the dynamic structure factor. So if you look at this in a plane that is maybe more familiar to you, so you have the momentum transfer as a function of the energy deposition, and this is a log-log scale. So typical materials with collective excitations, you'll be looking at momentum transfer, which is the interparticle spacing or the inverse interparticle spacing, and that puts you naturally in kind of this KeV spot. At higher momentum transfers, that's where you're in the nuclear recoil regime. And the response, the energy deposition, just scales like Q squared. But the issue is that you actually extract very small fraction of the dark matter kinetic energy. So that's what these gray regions are. This is the dark matter kinematics. So basically, you want to have an overlap of this gray region with some type of excitation in the material, whether that be a nuclear recoil, an electron transition, or phonon excitations in the material. And ideally, the higher up in the dark matter parabola you are, the larger fraction of the dark matter kinetic energy you extract. And so therefore, you're going to have a larger energy signal in your detector. Okay, so you want to have a good match between these parabolas and whatever excitations you have in your material. So another example of this, for example, is in superfluid helium, where you have these heat maps of the response of the material for a given momentum transfer and energy deposition. And you want to overlay that with the dark matter kinematic parabolas. Okay.
Can I ask you a question?
Yeah.
So this diagram that you drew, so that was like two dark matter particles coming in, two normal matter particles coming out. So it seems like in the center of mass of the dark matter, I mean, in principle, I don't need to have any momentum, right? It's just energy. So what is this relationship? I mean, between momentum?
Yeah. So okay, that's a good question. So dark matter carries a momentum in the Milky Way because the Milky Way has a virialized halo. So all dark matter experiments, what they're doing is taking advantage of the fact that the solar system is moving around the center of the galaxy, and dark matter is just virialized in our halo. So at any given time, dark matter particles are flowing through us with a velocity, which is the virial velocity of the Milky Way halo. And that's about 300 kilometers per second, or about 10 to the minus 3 times the speed of light. So dark matter is not just sitting there at rest. It's moving through your detector at this, it's still cold because this is a small velocity. But what you're trying to do is to catch a rare interaction of that dark matter particle with whatever excitation is available to you in your material. And it doesn't matter if it's a scattering process or if it's an axion absorption process. all dark matter experiments that are haloscopes will be doing this, taking advantage of the fact that we're flowing through dark matter constantly, just by virtue of the fact that we're sitting in our galaxy.
I see. So you're saying that the momentum is really coming from the fact that we're moving through this through the dark matter. And by the way, so why dark matter is not moving? How do we know that?
Well, it is. Yeah, there's both effects. So dark matter is virialized, and it just has an approximately Maxwell-Boltzmann distribution with an average velocity in that distribution, which is this 300 kilometers per second. And then you get a directional effect from the fact that which is to say the solar system, is moving around the center of the galaxy. And so there's actually a direction to the wind as a result of that.
So the dark matter itself is presumed to be fairly stationary, right? So it's not, so it's kind of like.
Yeah, the dark matter is got a Maxwell-Boltzmann distribution. So in the galaxy, it'll be totally isotropized or approximately isotropized. In practice, it's not actually totally isotropized, but it's approximately isotropized. But then there's a disk of the galaxy, and we're rotating in that disk, and that gives rise to a directional effect.
I see. Yeah, thank you. Any other questions? Okay, yeah, please continue. Thank you.
So the fact that dark matter has this Maxwell-Boltzmann distribution with an average velocity, which is 10 to the minus 3 times the speed of light, that's what fixes the shape of these kinematic curves. Okay, is just this curve here is just the momentum or the energy being mv squared, literally. Okay, so you want to have, so what you should notice is that, of course, heavier dark matter has more momentum and energy to deposit. So at higher energies, the relevant degrees of freedom are nuclear recoils. And then as you go to lower masses, lower energy, available energy, you'll have electron transitions that open up to you. And finally, you'll move into this regime where you'll get phonon excitations. So that's shown, that same information is represented a little bit differently here. So on the high mass end, there have been these searches for WIMPs through nuclear recoils. Here you're typically looking to extract KeV types of energy depositions in the process. Then as the dark matter mass drops below the target nucleus mass, so below the 10 GeV scale, then the relevant excitations are electronic excitations, and those are going to work as degrees of freedom all the way down to the EV energy resolution. So MeV dark matter, if you just take MV squared, that carries about electron volt energy resolution. So then as the dark matter continues to get lighter, then you start to open up collective excitations. And then this is really where all the material physics becomes rich. Because dark matter now, which is kiloelectron volt, will carry MeV, milli-eV of energy. And so if you have a detector that's sensitive to milli-eV energy depositions, then you can look for single excitations that will allow you to detect dark matter down to KeV. And now at this point, this is where you make a transition into a regime where you would be looking for dark matter not to deposit its kinetic energy, but instead to actually absorb its entire mass energy. So there's no V squared suppression, no 10 to the minus 3 squared entering anymore, but the entire mass energy can be absorbed. And this is the regime that's interesting for materials with axions. So in axion detection, you're not looking for a scattering event. You're actually just looking to absorb the entire mass energy. And then if you continue below the milli-electron volt scale, that's typically the ultralight frontier where the cavities become relevant. Okay. So you can now, for all these types of materials with a different energy resolution, you can compute what the reach is. Okay, and so here's an example. This is the target theory, and these are the purported reach through either phonon excitation, so that's the dashed curves, in different materials. So these are ordinary, I would call these all very ordinary materials, or through electronic excitation. And these thresholds where the curves, where the reach curves turn up, are set by the gaps, either the electron gap for electron excitation or the lowest optical phonon branch if you're going through phonon excitations. So target diversity in general is very important because the dark matter interaction is sensitive to the material type. And the simplest way to think about this is that the effective coupling between the dark matter and some electromagnetic current actually depends on the in-medium response. So if you have a large optical response in the material, the effective coupling of the dark matter to the visible sector can become strongly suppressed. And so this is the dominant, one of the dominant reasons that it's important to look at different types of materials. So the first thing that I looked at long ago was an aluminum superconductor, because those have small gaps. 0.3 millieV, I think, is the Cooper pair binding energy in aluminum superconductor. But superconductors are also extremely optically responsive. If instead you take a Dirac material, it has a lower number density near the Fermi surface, but it also has a much weaker optical response. And so when you compute the reach of a small gap material, like zirconium pentatelluride, you can see that over much of the dark matter mass range, you have a better sensitivity than with an aluminum superconductor. Now, one thing I'd like to say is that in these materials, the topological properties are not exploited. And I think one generally interesting question is, could they be exploited? Okay, and all these reach curves, we're imagining that somehow you're detecting single electrons in these materials. So coming back to the topic of the workshop on axion absorption, these materials that can be sensitive to dark matter scattering can also just absorb the mass energy. So you have this axion photon-photon coupling by a loop of charged particles. And if one of those photons is actually an external B field, you can actually just have the axion mix into a phonon polariton. And if that excitation is gapped, and in a typical material, there are many such gapped phonon polaritons, you can, in principle, absorb the axion directly onto that phonon polariton. And so the reach to the QCD axion, so this is the effective coupling of the axion to photons. This is the band, the axion band. And so if these curves, the reach curves, for these different types of target materials drop below the QCD axion band, that means you have sensitivity to the QCD axion. And you can see that by absorbing the axion into the phonon polaritons, you can reach this range of axion masses that correspond to the phonon polariton resonances. Another way that you can look for axions is through absorption on magnons. And the reason why you can look for axion to magnon conversion is because the gradient of the axion couples to the electron spin. Now, the challenge here is that the magnon that the axion couples to well is actually the acoustic magnon. It's the one that's not gapped. However, if you want to match the kinematics, you actually need that magnon to be gapped. So what people do sometimes is to put the material, let's say GIG, into an external magnetic field that creates a gap. And then by dialing the size of that magnetic field, you can scan in mass. And so here is an example of the range of couplings of the electron that you can reach, again, with a kilogram year exposure, background-free exposure of YIG in a 1 Tesla magnetic field. Okay, so this would be a very hard experiment. So what are other ways that you could look for axions through magnons? Well, you need to have a gapped magnon that that nevertheless still couples, has spins that precess in phase. And other ways you can do that is to look at anisotropic materials. So we looked at anisotropic couplings between the spins, which will allow the axions to couple to these gapped magnons. We gave a couple of other examples here, okay, where you could potentially reach the QCD axion. People have also looked at other types of excitations that you could absorb axions on. So this group of people looked at these. Is there a question on
Yeah,
this?
there is.
Yeah, Sasha has a question.
Yeah. So I missed a. When you look at the scattering axion of the magnon, this is not about
scattering, it's
the
absorption. It's not scattering, it's absorption. But yeah.
just absorption, just because of the kinematics. Okay. And what about the like you have a pseudoscalar particle disappearing, and then actually you have a magnon, you can probably excite magnetic excitation. Then how does the parity -1 actually works out for the magnon? Is just because of momentum in a certain direction, or how does it work?
Because it's the gradient of the axion. It's this coupling down here.
Right, but this gradient has to go into direction of the vector then?
Yep. So you can see I'm pointing at it with my mouse here. It's the gradient of the axion dotted into the electron coupling.
Yeah.
Electron spin. And so
Yeah,
then the
okay.
electron spin.
Okay.
Yeah. So the gradient
Got
of the axion actually behaves just like a magnetic field.
Got it. Thank you.
Yeah. Can you see my mouse? I've been assuming that you can see my mouse.
Yeah, we can see.
It's like barely. There is an option to do the mouth, which is actually like a red dot, because this is a, yeah.
Oh.
I don't know if there is a way to do it.
Yeah, we should be probably wrapping up in a minute or two, and then to leave just a bit of time for questions, and then we can have deeper discussion later on.
Yeah, so this antiferromagnetic topological insulators, this is a more exotic class of models. So here it's a little more involved. The axion mixes into an induced electric field, which then induced into this axionic degree of freedom, this spin wave. And then they want to read this out by having this through the boundary conditions, have it convert to a terahertz photon. And their claim is that they can also reach the QCD axion through some of these through materials with the spin wave type excitation. All right, so I'm gonna jump ahead and just say that the observational challenge is that you need targets that have low dark count rates with low energy thresholds and good resolution, and superconducting detectors that are currently being developed by the dark matter community include MKIDs, SNSPDs, TESs, and these QCDs. And I think it's kind of a horse race to see what ends up being the best for having excellent energy resolution and low dark count rates. And this is just to say that there's a lot of activity going on. And so what we're trying to do then, just to go back to the initial picture, is extend from this focus on the weak scale to lower mass dark matter particles, which means that we need to, really focus on the material properties that are best suited for the dark matter kinematics and interactions. So I'll stop there. Thanks.
All right. Yeah, thank you very much for a great overview. So we have a couple of minutes for questions.
I have a question. Hi, Professor Zurich. Thank you for the really nice talk. I was wondering how one determines how, or rather what type of axion to quasi-particle couplings are allowed, and how you kind of determine which quasi-particles it can couple to. Because I know you mentioned that, I think you gave the example for the magnon that it can only couple to the acoustic magnons.
Yeah.
So I was wondering how one determines which of those couplings are allowed.
So there are some general principles, like the one that I mentioned, that the gradient of the axion behaves like an external magnetic field, and so therefore it couples most strongly to the magnons that oscillate in phase. And so therefore finding a coupling to a gapped magnon becomes challenging. Practically speaking, so there are some general principles that you use, just like the kinematics and what we know about the kinds of excitations that couple to things like photons and magnetic fields. But in practice, of course, what you do is to just sit down and calculate it, right? You know what the Hamiltonian is, and you have some model, let's say, spin model, or lattice model for the ions in the unit cell. You get the Born effective charges if you want to compute, let's say, the couplings, so that, to compute the phonon eigenenergies and their eigenvalues. And then you run it through program, like PhonoPy if you're interested in phonons, or you write a program that does the same type of thing, but for the spin couplings in the case of the magnon. And then you extract the effective coupling because you know what the dark matter Hamiltonian is. So the answer to that question is, we have some papers where how you calculate that in detail is laid out, in a great amount of detail. I just didn't happen to go through those calculations.
Sure. Okay, thank you very much.
Any other questions? Okay, so maybe then we can have more discussion. I certainly have more questions, but we can leave it off for a discussion that we're going to have afterwards. So our next talk is going to be by Aaron Chow from Fermilab. So Aaron is responsible for for all the data analysis for ADMX experiments. So it's really exciting to have him here. And the topic of his talk is going to be searching for the QCD axions over 9 decades in mass. Thank you, Aaron.
Hi. Yeah, thank you, Ivar, and thank you, Peter, for the opportunity to join this very fun event. So I'm going to not go too much into technical details in this talk, but rather give kind of a global overview of I and some of us in the high energy physics community are viewing the search for the QCD axion. I mean, the community has been trying to find this kind of axion and dark matter for almost as long as the condensed matter community has been searching for quantum spin liquids. And so we really want to try to bring this forward to the end game if we can. And so I'll give you an idea of what kind of challenges we face, and then have a little bit at the end about how the quantum materials community could help, in addition to what the excellent points that Catherine has already brought up. Okay, so just a quick reminder, the QCD axion was motivated by a strong CP problem, which is a cryptic name for this problem of the non-vanishing of the neutron electric dipole moment, where if you think of it's made up of charged constituents, then unless for some reason these charges are very symmetrically distributed, you would expect some kind of charge separation and an electric dipole moment that would emerge on the size scale of the neutron of 10 to the minus 15 meters. And there have been now more than 70 years of experiments searching for a non-vanishing neutron electric dipole moment, starting with the pioneering experiments of Norman Ramsey et al. In the 1950s. After more than 70 years, we're still going at it. The apparent, the upper bounds on the neutron electric dipole moment are now 10 orders of magnitude below the naive expectation, corresponding to this CP or T violating angle of being 10 to the minus 10 or less rather than the naively expected value of 1 radian. Okay, so this, I think, as far as I know, this is the longest standing problem in fundamental physics, even longer than the problem of dark matter, which I think wasn't firmly established until Vera Rubin's observations in the 1960s and 1970s. Okay, so 2 very, very long-standing problems in physics. Roberto Peccei and Helen Quinn in 1977 came up with a very elegant cosmological solution in which they postulated that there's some potential energy function given here by this Landau-Ginzburg potential of a complex scalar field. Complex scalar field is like a proto-axion, it's dynamical. And the idea is that first, there's some global symmetry breaking that creates the axion as a massless Goldstone boson running around in the valley of this wine bottle potential. And then they postulated some coupling of the phase of this complex scalar field to the gluon condensate that emerges during the quark-gluon phase transition. And this ends up being a term that's linear in this phase. So from the point of view of this picture, it's like this wine bottle potential got tilted by an amount equal to the energy density during the quark-gluon phase transition, or lambda QCD to the 4th. That causes this scalar field, this order parameter, to roll down to a unique minimum of its potential energy, at which the total CP violating angle vanishes. That zeroes out the neutron electric dipole moment, solves that problem. And because this ends up, if it's a very light field, there's no way for the kinetic energy in the oscillations about the minimum to decay away on the scale of the lifetime of the universe. So the original energy density in the quark-gluon plasma then becomes the power source, or the energy source, to populate the dark matter of the universe. Okay, and so the dark matter has a mass that's related to the second derivative of the potential about its minimum. And so if you want to write that down, that'll just be that'll be related to the amount of the tilt and the kind of the energy scale or the temperature of the original phase transition, which is completely unknown. So of order 10 to the 9 GeV could be greater, could be less, but the mass will just be this combination of these energy or temperature scales of cosmological phase transitions. Okay, so that's just a lightning review of the Axion model, explains the vanishing of the neutron electric dipole moment and provides the energy source for the dark matter. Okay, so the Axion dark matter that we would observe in the galaxy because it's the locally coherent oscillations of that QCD theta angle. So imagine all of that internal kinetic energy, it couldn't decay away, so it's hanging around in the universe. And what's more, because of the Jeans instability, this energy collapses and forms gravitational potential wells and further concentrates that energy. And as Catherine mentioned, for very low mass particles, these have to be bosonic. So they're very high occupation number modes, just very much like what you get out of a laser beam. And so these coherent oscillations allow the coherent field to undergo excursions about the minimum of the potential to a point where the potential energy becomes equal to the internal kinetic energy, which is pretty much the mass density of the local axion field. And if you work out the numbers, the excursion in the CP violating angle is of the order of 10 to the minus 19 radians. So this is what we're up against. We're trying to measure an extraordinarily small angle. I'm not aware that anybody has ever measured such small angles before. For comparison, I think LIGO measures phase modulation of angles of order 10 to the minus 14 radians. Okay, so this is far more challenging problem than what anybody has ever tried to do before, and that explains why we've been searching for the axion for about 40 years now. So a couple of properties of this beam, and I should mention, if you have questions, you should probably just speak up. I'm not necessarily able to see raised hands. So the source of the signal can be described as follows. It's a classical wave of the CP violating angle. It has macroscopic occupation number. Just put in the numbers that you get close to Avogadro's number or somewhere about there of individual axion particles in the coherent wave. As Catherine mentioned, this is the individual particles are all non-relativistic because they have to be bound by the potential well of the Milky Way galaxy, and the escape velocity is of order 10 to the minus 3 c. So the velocity relative to the solar system is around 10 to the minus 3 c, and the dispersion in the velocity is also about 10 to the minus 3 c. That tells you that the energy spread relative to its mean energy, so it's non-relativistic, so its energy is dominated by its rest mass, and the spread in its kinetic energy, a ratio of that to its rest mass is 10 to the minus 6. That tells you kind of the line width of the axion. It has an effective quality factor of 10 to the 6. Okay, so these are all properties of the beam that we're looking for that are fairly generic. And then the other thing you can note is that the coherence length then will be 1 over the velocity dispersion. And given that this was 10 to the minus 3 c, this is about 1,000 wavelengths. Okay, so
Question.
Yeah, please.
So this is probably a question of language. You pointing out the laser pointer analogy. Is the assertion then that the theta, I can view theta as essentially the macroscopic Bose condensate of some particles?
Yes, I think
Macroscopic occupancy number.
Yeah, we generally model it as a coherent state, just exactly the same way that what's coming out of the laser is a coherent state. That's right. So it's a plane wave.
Sorry, and I have a question. Go ahead.
Please go ahead.
No, you were in the middle of something, but I have a question. Just
Oh,
finish,
okay.
please.
Yeah, we just think of it as plane waves that are coherent over an extent of 10 to the 3 wavelengths, and then have a fairly narrow bandwidth. So if you think about a laser, the line width of a laser kilohertz line width, the dark matter line width is comparable to that. Yeah.
And you have a coherence length much longer. What is the wavelengths typically here?
So the wavelength might vary over 9 orders of magnitude, and
Depending
that's
on mass,
the real challenge. So any kind of sensor that you make is probably only good for over a factor of 2 in wavelengths to match energy scales and distance scales. If you're going over 9 orders of magnitude, you have to have a collection of very different kinds of detection technologies.
Yeah, so but the wavelength is standard wavelengths I can do from some visualized temperature, mass, and all that. Basically,
it really kind of depends on what the initial phase transition temperature scale is. So if I skip ahead a little bit, we're kind of looking for masses ranging from 10 to the minus 1 electron volts all the way to 10 to the minus 10 electron volts. So this is a very, very large
there's a huge range,
lengths from 10 microns up to hundreds of meters.
Thank you. Okay.
Other questions? Sorry, you said something about angle measured in LIGO. What angle in LIGO?
LIGO senses strain via the change in the relative arm lengths of the 2 arms in their L-shaped interferometer. And so I'm talking about the phase angle that they measure when they are looking when in their interferometer.
But that's some physical phase of the instrument. But I thought this is just this is the axion angle here, which is not obvious how it relates to any physical observable unless you said it.
I'll get to that. I'll get to that in just a second.
Oh, it just seemed like apples and oranges comparison, 10 to the 19.
Yeah, from my point of view, all angles are angles, and you can change one angle to another, and in the end, when you measure them, it's all the same from the point of view of an experimentalist.
Oh yeah, okay. In condensed matter, for the condensed matter experiments we talked about this morning, there's a Faraday rotation, which is the rotation of light, which is small, which is of order of the fine structure constant, and then there's the axion angle, which is pi. So these are different.
Right. Yeah, but again, I would say all angles, when you try to measure them, you're stuck with the Heisenberg uncertainty principle, the photon number phase uncertainty relationship, and that determines your sensitivity.
So this is more for discussion, Peter, but per your question, these are oscillations of theta. This is not the theta itself. These are ripples on your theta.
Yeah, so theta.
These are collective modes of theta.
That was my question to him. But he was saying all angles are the same, which is my confusion.
Yeah. And then there's waves of some very low momentum going through the galaxy whose energy is dominated by the non-relativistic rest mass. Okay, but it's oscillations, it's oscillations in the amplitude of this CP violating angle that we're looking for.
Okay. I
Okay.
have questions. I'll wait. Go ahead.
Okay, very good. So sorry, this should be theta over here instead of A. Sometimes people write A. A is the theta multiplied by the initial temperature scale. But what happens is this angle comes in, and through the topological magnetoelectric effect, it rotates magnetic fields into electric fields and vice versa. And so the way that the experiments work is they employ these, many types of experiments work is they employ this three-wave mixing process, and you apply a very strong magnetic field in the laboratory. And as the dark matter comes in, it'll rotate that magnetic field into electric field in the form and create single photons whose frequency is equal to the energy or frequency of the original axion wave. And so the experiments work by creating some kind of resonator, high Q resonator inside a refrigerated Faraday cage where external disturbances are efficiently reflected off, but nothing can shield against the dark matter. So dark matter wave enters. There's a strong magnetic field in the region. It gets rotated into an oscillating electric field. That oscillating electric field excites the resonator, and then you read that out with a very low noise sensor, like a quantum amplifier or a qubit or something. And then you can estimate the signal rate just based on this diagram. It's going to have something to do with this coupling. It's a three-wave mixing process. So it's going to have something to do with the amplitude theta of the incoming dark matter wave. And it's going to have to do with the amplitude of one of the two photons in the mixing. And you have to square the matrix element. So this is squared, and you multiply by volume, and then you multiply by the quality factor of your resonator. And if you work this out, you'll find that your signal rate, the rate of signal photons coming out, is going to be proportional, linearly proportional to the stored magnetic energy in your device. Okay. And again, the signal is you have a very, very cold resonator in here, and very occasionally the dark matter will succeed in depositing a single photon in this device where previously there was none. If this was a quantum computer, for example, mysteriously you did not populate the RAM with quantum bits, but mysteriously bits of information have appeared populated by the dark matter. Okay, any questions at this point? I'll just barrel on ahead then. As I mentioned earlier, we have no idea what the mass of the axion is, but we do know it's kind of, this is a plot on the vertical axis. It's the coupling to two photons, where it's weighted by 1 over the original temperature scale. And then this is the mass, the unknown mass of the axion. And as I said before, the mass and the coupling scale are related to each other linearly. So the prediction is that if you normalize this to the strong force, so that this can solve the problem of the vanishing neutron electric dipole moment, then you're lying somewhere in this shaded region in this plot. And the goal is to create an experiment that has sensitivity to these rotations of magnetic field into electric field that's predicted by this model. We don't know, this range is kind of given by the fact that as you go to too high in mass, eventually you hit other limits having to do with star cooling, where the stars would cool by emitting axions instead of the thousands of years, whatever it takes for photons to random walk to the surface. They would cool too quickly if the couplings to axions were too strong. And if you go all the way to the left on this plot, eventually you hit the point where the initial phase transition scale of that Landau-Ginzburg potential exceeds the Planck scale of gravity, and then we don't trust our effective field theories anymore. And so that kind of gives us the range of axion masses that we have to search. And very few experiments have succeeded in even touching this predicted axion band. I work on one of them, the axion dark matter experiment. And the issue is that, again, these experiments are very narrow band experiments. We're relying on high Q resonators in order to enhance the signal, to narrow band the detection bandwidth, reject noise. And as a result, it's a slow radio scan going step by step through frequency space, very, very slowly. This is after like 3 years of effort. We just nibbled off a little bit here. And the point I want to make eventually is that the radio scan speed, I told you the signal rate is proportional to the magnetic energy. So the speed at which you can scan through these 9 orders of magnitude is at least linearly proportional to the investment that you make, how much money you spend on magnets to induce this 3-wave mixing interaction. So for example, ADMX has 1 magnet. If we had 10 magnets instead of 1, we could go 10 times faster, or we could buy big magnets, or we could do both. And so I'm going to talk a little bit about what the strategy should be moving forward if we do want to cover this entire range within our lifetimes. Okay, and this is just a point that there's many proposals coming from all over the world that can largely cover this entire range. There's a small gap here at about 100 gigahertz where we don't know what to do, but otherwise the technology is coming together, and all we need are the big, extremely expensive magnets, and I'll try to motivate that. Okay, so here's a picture of the ADMX resonator. It's a cavity of about 50 centimeter size to go after the 1 gigahertz or 4 micro EV mass axions. So the size of the cavity is roughly the wavelength of the incoming dark matter wave. So as the dark matter wave comes in, it scatters off one side of the cavity, creates an electric field that traverses to the other side of the cavity and bounces and comes back. And it comes back in time with the next wavefront, the next crest of the dark matter wave. And so it's kind of like slapping a ping pong ball back and forth and just keep on hitting it, and it builds up energy. But because we do need to tune over a fairly large range, the only reasonable way to do it is to actually change the boundary conditions by moving conductors around inside. So you perform the radio scan here with a movable tuning rod. So this is fine for these kinds of cavities where they're kind of meter scale. You only have 1 cavity and only 1 part to move. As you go to higher and higher frequencies, the size of the cavities shrink. And then to get the same total volume to intercept the same amount of dark matter that's coming in, you start needing hundreds or thousands of cavities, and it becomes prohibitively expensive to instrument. Okay, and that's, in the end, that's where some of these ideas of using exotic modes in quantum materials or even in regular materials might be useful. Okay, I do want to mention we typically have meter scale magnets, but then the wavelength of the dark matter could be hundreds of meters, and so you're kind of in trouble. So if you here, I have a cartoon of a dark matter wave traversing through a meter scale magnet. And so what happens then is instead of measuring the full kind of electric field induced by the dark matter, the peak-to-peak value, you only sample a small portion of the excursion of the amplitude, of the electric field amplitude that's generated. And so you're kind of suppressed. The size of the cavity acts as a high-pass filter that filters the signal, that suppresses the signal. And there's really nothing you can do about that. We cannot make magnets that are hundreds of meters large, but it's just something to keep in mind. Here's a picture just to set up my colleague Dave Schuster's talk that's coming up next of an experiment that we're doing in which we have a photonic bandgap cavity. I was talking about magnetic bandgap materials, but this is a photonic bandgap material on the left, in which the Bragg scattering off of each cylindrical surface adds coherently to reflect the wave inwards and keep it away from the lossy copper walls of the enclosure. Okay, this is very, very low loss sapphire dielectric. And using this technique, we can achieve a very, very high quality factor resonant mode that lives in the center sapphire cylinder, where the quality factor is matched to the quality factor of the dark matter. This then goes into a 10 millikelvin dilution refrigerator. So here you see it mounted here as kind of a centimeter scale cavity going after 10 gigahertz photons. And then there's a magnet that lifts up and surrounds this cavity. And again, the axion dark matter comes in, scatters off the cavity walls, deposits occasionally a single photon. The single photon is extracted into a remote cavity shown here, something similar to this, in which we use a single superconducting qubit to sense the photons, the signal photons. And again, can postpone questions for the next talk. Dave will presumably tell you all about this. Okay, so I want to bring up another point that your axion, because we are instead of just doing 2 proof of principle experiments, we are trying to cover 9 orders of magnitude in mass parameter space. We have to be a little bit careful about how we budget our time. Okay, so if we think about it, your sensitivity is going to be determined by how long you have available to integrate for the experiment after you put the experiment in each individual tuning configuration. You're going to tune it to one frequency, integrate for some amount of time, tune it to the next frequency. So if the quality factor is 10 to the 6, and you have 10 to the 7 seconds in 1 year, then probably if you want to go through 10 to the 6 tunings to go in a factor of 2 in frequency or a factor of 2 in mass, the maximum you can budget is 10 seconds at each tuning. Okay, so this is something that people don't often understand, that an Axion experiment is not one experiment. It's 1 million experiments, each of duration 10 seconds. And for each experiment, you have to do the calibrations. So it's very, very difficult. The other point I want to make is here I'm plotting the photon rate, whether it's from signal photons, that's the black line as a function of frequency, or background photons, that's the blue for standard quantum limit, or red for dark rates for various kinds of qubit detectors. I'm plotting the rates of photons versus frequency. And as you increase in frequency, I already mentioned the cavity size becomes smaller and smaller, so you intercept less and less of the dark matter. So the signal rate plummets like this. And then the issue is that if you only have 10 seconds to integrate, and you want to have a statistically significant signal, you better count at least 9 or 10 photons, because that 9 photons can fluctuate down to 0 photons with 3 sigma, with a 3 sigma fluctuation. So about 1% of the time you'll lose it. Okay, so you better count at least 10 photons, and you only have 10 seconds. That means the minimum detectable signal rate at 3 sigma significance is 1 hertz. Okay, so that tells you that for this particular experiment, this particular combination of magnet and et cetera, above about 20 gigahertz, you run out of signal and it just doesn't work anymore. In general, this is going to be an issue. And again, this is the issue of scaling to very high frequency, small wavelengths. You instrument lots and lots of little cavities, or do you eventually move to some material target? Okay, so the way that we work with the higher frequencies is, of course, we're not going to instrument a million different moving parts. Instead, we do broadband searches by replacing the temporal periodicity of the resonators, where you're bouncing back and forth between 2 mirrors, with just a single bounce off of a single mirror, a dish antenna. So you can think of these as Q equals 1 cavities, but then do spatial power combining of the electric field wave that emerges. And because it's non-relativistic, it does not uniformly populate phase space. The direction of the outgoing plane wave is just normal vector to this dish scatterer. So you can focus these electromagnetic waves down to a single mode detector and replace the temporal periodicity with spatial periodicity. So advantage of this is, in effect, you've made your experiment far more broadband, which means you're no longer limited to just having 10 seconds per integration. You can now conduct this experiment over a year or 3 years or whatever, and so you're no longer limited by low signal rates. Okay, so an example of this is the bread experiment. I won't go into detail on this, but again, it's the Axion photon coupling versus the Axion mass. Except now we're going to fairly high frequencies. Before I was talking about like 10 gigahertz. Now we're talking about terahertz, tens of terahertz. And so again, this diagonal band is the target where the QCD Axion model lives. And so the point here, just to give you some numbers, we have this quantum capacitance detector that Catherine briefly mentioned. Dark count rate is about
Is Saren frozen? Can everybody hear the audio? Somehow my audio
Yes.
disappeared.
I can't hear
No, I
either.
can't hear you.
Oh boy.
Okay, now I
Okay.
think it's fine. I think it's good.
Okay, why don't I turn off my
The
video?
whole thing went away for a minute and now it's back.
Yeah, something like that. Yeah, about a minute. Well, maybe 30 seconds.
Okay. So I guess I just want to point out from this, I won't go through the numbers again, but I'll just point out that we're still talking about fairly low signal rates. So for an experiment that takes 3 years, 10 to the 8 seconds, we're talking about a signal rate of 10 to the minus 6 hertz. That's 100 counts in 3 years, and on top of 10,000 background counts. And that's kind of what we're looking for. And this seems pretty marginal to me. This seems extremely challenging, I would say, to get the background count that low, or to see a signal rate of a couple of counts per month of terahertz photons. When was the last time that you had a terahertz background that low? And so the point is, for both types of experiments, resonant experiments and these broadband dish antenna experiments, I think we really need to try to boost the signal rate, because we cannot rely on the background rates being suppressed by such large factors. Okay. People still there? Yeah, okay. All right, so what we really need are big magnets. So here's a table of different magnets, both existing and proposed, and I've highlighted some of the existing magnets that we're using. So we have the magnetic field, the various size parameters, the various figures of merit that determine the signal rate, like b squared times the volume, b squared times the area, the stored energy, and the particle physics accelerator community has come up with scaling formulas for how much a magnet costs per megajoule of energy. So in this last column, I have the cost of the magnet. Okay, so the point here is that the current magnets are these kind of meter scale nib tie magnets, 8 Tesla. They cost about $5 million in today's dollars. The one that we're about to deploy for the next experiment at Fermilab is about a factor of 2 higher in cost. Luckily, it's like a factor of 4 or so greater magnetic energy. So it's better than nothing, but it's not quite an order of magnitude. And then we also have the magnets that they use in the collider experiments that really are a couple of orders of magnitude larger, and also a couple of orders of magnitude more expensive. So my point here is that the next generation of experiments are kind of focusing on the $10 to $50 million scale magnets. And my assessment is that these experiments will barely reach the Axion with a lot of perhaps over-optimistic assumptions about how well you can lower the background rates, the noise rates, and to really decisively reach the Axion in our lifetimes, we need to move to the next scale of magnets that are being used in the collider experiments. And then beyond that, if we discover the Axion while using this kind of $100 million scale magnet, the next step is if we really want to understand its properties, then again, we need to take the next factor of 10 in sensitivity and move to kind of the kind of magnets that they're using for plasma fusion. Okay, so again, this is the history. I mean, this is actual data that people have compiled about how much magnets have cost. This is in 2017 dollars, I believe, and the most expensive ones are the ones that are being used in the high energy physics community for the big particle detectors at the cost of $100 to $200 million. Okay, so that's a lot of money, right? So here's a picture of the CMS detector, and my point is we don't need just one of these, but we need multiple copies of this if we want to get through 9 orders of magnitude in mass parameter space. If the costs weren't bad enough, the other point is that each of these magnets takes 10 years to build. So if we want them, or we think we might want them 10 years from now, we better start planning today rather than wait 10 years. So given that the magnitude of this endeavor, then we have to start thinking about, who are their partners going to be? So one immediate partner that jumps to mind are the people who want to build the muon collider. And the muon collider starts with a proton beam that creates a pion beam that's later going to decay to the muon beam. And so you have a megawatt pion beam hitting some target, and you want to focus the hadron beam hitting the target to create pions, and you want to focus those pions down so that you can capture the muons. And what they're thinking about here is a 2-meter bore 20 Tesla magnet of the type that we don't even know how to build yet. And that's what they need. But given that it takes 10 years to build and it takes 20 years to build a muon collider, perhaps they could build that magnet first, and then we could use it for 10 years before they get first beam. So this is the kind of thing we're looking at. And in general, I've gone through and engaged the various communities that might be interested in such magnets to try to build a coalition to have at least a detector, a magnet R&D program, so that we are able to build these magnets once we're ready to argue for them. And this includes not only the muon collider and Axions, but also the rare and precision frontier, which needs intense muon beams. And then from the non-HEP folks, there's the plasma fusion people, the people who want to do high field MRI, who want to do crystal growth in magnetic fields, and also want to study quantum magnetic materials inside large bore magnets. And what would be really helpful is if the other folks here in the condensed matter community could think of other useful applications that we could add to this list. That would be very useful, I think. Okay. So then lastly, I want to go to this point of that was mentioned earlier in Akihiko's talk, and also in a couple of the other talks today, of scattering the dark matter wave off of some topological material that has some internal resonance, which that can be used to enhance the scattering process. So this is like making millions or billions of tiny little cavities inside the material. And then the point is, not only do you need those resonances, you also need them to be tunable. And Catherine also already mentioned that for some of these, if you apply a magnetic field, you can tune those resonances so that you can tune them into resonance, convert the dark matter wave into photon waves, and then count them with some kind of low noise photon counter. Okay, so then the question is it really worth doing this? I'm going to argue that it is. So can we quantify how much it is worth doing this? So we'd like to make resonant dish reflectors out of these exotic materials, and eventually we want them to be tens of centimeters in size, if not meter scale. They don't have to be like a full single meter scale crystal. You can make them out of little tiles of high quality crystal if you like. But is it worth doing it? And more generally, is it worth doing other things like lowering the dark count rate with the quantum sensing techniques that Dave will discuss in just a couple of minutes? Okay, so the way to think about this is that if you want to do a 3 sigma detection in a photon counting experiment, you want the signal rate to be greater than 3 times the geometric mean of the background rate and 1 over the time. So essentially, this means that you want the number of signal photons to be greater than 3 times the number of Poisson fluctuations in the number of background counts. The signal rate, as I mentioned before, is going to be this combination of this coupling constant times the amplitude of this axion wave in the 3-wave mixing process, this quantity squared, multiplied by the total energy stored in the magnetic field. Okay, so then what happens if you're able to make this previously non-resonant dish reflector slightly resonant? That kind of gives you a factor of the quality factor of the resonance, enhances the signal rate by that much. The background rate is just some external photon detector, some broadband photon detector. So in this case, the background rate is unchanged. But then you have some fixed amount of time to cover your 9 orders of magnitude in parameter space. And you're not going to, if Q is 10, you're not going to be able to convince the funding agencies to give you 10 times as much time, 10 times as much money. So you assume that because this thing is kind of resonant, the frequency coverage now is down by a factor of Q. So you have to tune Q times to get the same frequency coverage as before, but you have the same total amount of time. So the time you have available for each tuning, the integration time you have, now has to be down by a factor of Q. Okay, so we plug that in. The signal rate increases by a factor of Q. This is the second equation. And the amount of time you have decreases by a factor of Q. That's what I have under the square root in the second equation. And then I solve this for G squared, the coupling squared, which is kind of what we're trying to measure. And we find this formula here, where we still have the magnetic energy in the denominator, and then it's a square root of the background rate divided by Q. Okay, so this is quite interesting. This means that if you increase Q by a factor of 10, that means you're allowed to reduce the magnetic energy by a factor of 3. Similarly, if you reduce the background rate by a factor of 10, you can also get away with reducing the magnetic energy by a factor of 3. Okay, so this is huge because that, remember, the cost scales as magnetic energy to the 2/3 power. So 3 to the 2/3 is 2. You've now reduced the cost of that magnet by a factor of 2. And that magnet, remember, the cost was measured in hundreds of millions of dollars. So even that mild resonance, if you can get us a factor of 10 in very high quality tiled crystalline materials, that saves us $125 million. Okay, so that's my punchline. That's my last slide. That
Excellent.
Even though you might be skeptical about the worth, at least for this application, it's worth a lot of money.
Excellent. Yeah, thank you so much, Aaron. So we have time for a couple of questions, quick questions, and then we can postpone the rest for the discussion.
Aaron, just one. I'm very ignorant about this, but I'm wondering if the dark matter axion is. So I know that the axion was initially studied in the context of this QCD neutron magnetic dipole, electric dipole problem. But the dark matter axion, is it the same axion or it's a different particle? Or
yeah, it's the same axion. I think Peche and Quinn first zeroed out the CP angle in the strong force. And then I believe Wilczek and Weinberg separately pointed out that, gee, if you have a minimum of a potential, then you have the quantized excitations. That's a new particle. Then I believe Wilczek pointed out, well, gee, we also have an energy source of that populates this potential, and there's no for sufficiently low masses, there's no way for this energy to decay away, so it must still be hanging around. And then therefore it must be the dark matter. There's no way.
So if somehow people observe the axion particle, then that it's a solution to both dark matter and also the strong CP problem at the same time.
Yeah,
can I understand that way?
Yeah, that's right. I think people will get very excited and then start testing the hypothesis that this particle that you discovered is actually the one that's responsible for zeroing out the neutron electric dipole moment.
I see. Thank you.
Thanks.
So you made this provocative point that let's say you have your quantum computer and then suddenly, let's say, a bit flips, and that could be an axion. But I guess in principle it could be like and most of the time it's a bunch of other things. So do you think it's actually practical to use some of those sort of fancy devices in order to
yeah, Dave will talk more about this, but that's all about lowering the background rate. So there's already bit errors in the quantum computers. They're not dominant, but they're already present. And just like there are bit errors in classical computers. And so as the quantum computing field progresses, presumably they'll reduce the bit error rate by a factor of 10, and then that might automatically get us a factor of 2 in cost for the magnets.
Mm-hmm. Okay. Any other questions?
Can I ask a question?
Of course.
Yeah. Hi. I'm still a student, by the way, and my question is, since the axions cannot be shielded, so they exist all the time, then how do you get the background? Because I mean, for a simple device you can shield it and you get the background, but if it's on all the time,
that's an excellent question. For the resonant experiments, this signal only appears at a single frequency, and so that's how you can tell that's not some broadband background. The second test you can make is the three-wave mixing interaction requires the DC magnetic field as one of the three waves. So you can turn off that magnetic field and see if that signal disappears. And you can see does the strength of the signal, how does the strength of the signal depend on how large the amplitude, how large that magnetic field is. So there's various things that you can do. So it's not going to be a case where you see a strange signal and you immediately write a press release and book your ticket to Stockholm. There's a number of different. Then there's couplings to electrons, as Catherine mentioned, and there's an oscillating. The neutron electric dipole moment would also be expected to oscillate at the same frequency. So you would have a large number of follow-up measurements to perform. And that's why I was motivating that once you see the first signal, you really need to then spend another factor of 10 more and get the next bigger magnet to conduct these follow-up experiments.
I see. And a simple follow-up question would be, are there any like materials, maybe even fictional materials, like a wall of neutrons or whatever can shield the axions? Just out of curiosity. Yeah.
Yeah, I'm not aware of anything that can shield the axions or dark matter of any sort, just because the interaction strength is just so weak. So we're talking about like Avogadro's number of axions coming in per second, and then once per month, one of them converts into a photon. So the scattering rate is extremely small. You just can't shield them. If it turns out to be an issue for future quantum computers, you would just have to make sure that the quantum computers are operating at frequencies that are not the same as the dark matter frequency. In the same way that you want to avoid various communication channels when you're operating any kind of experiment.
Thank you.
Right, thank you, Aaron. Okay, so in the interest of time, let's move to the next speaker. And again, we'll have longer discussion later. All right, thanks. So the next speaker is going to be Dave Schuster from Stanford.
Okay, I think someone needs to let me share screen. Okay, okay, good. Okay. Minimize this. And pointer. Okay, great. Can everybody hear and see me and everything?
Yes, please, go ahead.
Great. Okay, so yeah, so I'm going to be telling about a joint project with Aaron where we're trying to, at least in the microwave range, lower the background by using qubits as detectors. And this work was primarily done by Akash Dixit and Ankar Agrawal in terms of the work that I'm talking about, and Morgan and Fang are currently working on it with Watson and Tanai helping out. Okay, so I don't have to go into, Aaron already told you a lot about Axions and the general idea. The basic idea that we're pursuing is this cavity type detection where you put a cavity in a big magnetic field and an axion can come in and spontaneously convert into a photon. And as he told you, the signal rate is maybe order once per in 10 seconds or that kind of range. And so the question is, how can we detect these photons once they're there? So in some sense, for me, the axion is just a way of spontaneously producing these photons in the cavity. And then the question is, how well can we detect them? And can we eliminate all the backgrounds and things like that? And so in microwaves, usually you use a low noise amplifier to measure a signal. Well, a classical amplifier is always going to add some noise, and that's background, and that's bad. But it turns out, even if you had a perfect amplifier, given by quantum mechanics, there'll be some limits. As Aaron mentioned, the volume also shrinks at higher frequencies. And then another issue is that we have these large magnetic fields that are required for the axion conversion, but that means we can't use superconducting cavities. So that's an issue as well. So in terms of the amplifiers, even if we had an absolutely perfect amplifier, the ideal limit of a quantum mechanical amplifier, if it can detect both the phase and the amplitude of the signal, that's like detecting momentum and position at the same time. And so there's an uncertainty principle, and you get 1/2 of a photon of background. So that means that while our signal is going down as our frequency is going up, our noise is also going up, and it's sort of fixed. There's, no matter how cold we get or how low the signal rate is, we have some fixed background. And so that's bad. If we could make a photon counter, you can get around this. And the way to think about it is that we still need to have this h⁻²2 uncertainty. That's just, but if we made it into a ring, we could learn sort of have perfect information about the amplitude and nothing about the phase. So we still have uncertainty, but it's not in the thing we care about. So that's great. We can measure the amplitude of a signal. This is how, of course, all normal detectors work. You usually use an APD or photomultiplier tube for particle detection. But in the microwave, it turns out that this photon counter until qubits didn't really exist. And so most of this talk will be like, how do we make a photon counter out of a qubit? So basically, we're going to talk about how we can turn these qubits into photon counters and to get around this half photon of noise. And that's going to give us a very big speed up. It's kind of it's a very quantum thing we're doing. We're going to use all kinds of quantum optics to do it, but ultimately we're just making a photon counter, which everybody's used to even before sort of qubits and quantum information and stuff. But then we're gonna even use some more quantum optics and actually use stimulated emission to not only enhance the to lower the background, but maybe enhance the signal a little bit. And then Aaron mentioned it, but I'll also just briefly show you a picture of this photonic bandgap cavity we're making to try to have a high Q cavity in a large magnetic field. Okay, so here's kind of a schematic of our device. And so we have basically we have a qubit, and it's coupled to two cavities. One is our kind of transduction cavity. And this is where, dark matter could potentially spontaneously convert into ordinary photons. And we want to detect those photons. And then we also have another cavity that just reads out the qubit. And this is a kind of a schematic of what it looks like in terms of, in terms of Hamiltonians. So we have a harmonic oscillator. That's our box is a harmonic oscillator. That's this term. We have a qubit, which we can model just as a spin. It's a little bit more complicated, but mostly we can think of it as a spin for these purposes. And they're coupled together, in such a way that basically, if you put a photon in this box, it shifts the qubit frequency a little bit. So let's look at the qubit a little bit more. So the qubit we use is very much like an LC circuit, so it has a capacitor. But instead of having an ordinary inductor, it uses what's called a Josephson junction, and a Josephson junction looks like this. It's two superconductors with a very thin insulating barrier, and you can see there's sort of two fingers, one on top of the other, and in between there's this is kind of what it looks like in an SEM. And in between these two is a very thin oxide barrier. And that looks like kind of like an inductor. And so you can, if an LC is a harmonic oscillator, you can sort of think of that as like, kind of some parabolic potential. And the states are, 0, 1, 2, or G, E, F, if you like. And the thing about this, this Josephson junction is it's a very nonlinear inductor. And it's so nonlinear that, in fact, adding one extra photon will shift the frequency by a few %, so that we can sort of take this GE and we can kind of manipulate it independently of this EF. And so that's going to allow us to treat it like a qubit. And we're going to use this guy and its interaction with the cavity to actually do our detection. So we're just going to stick it in the cavity. I kind of showed you maybe a more detailed picture before. and the and basically there's an electric field in the cavity from the photon, and then this thing looks like a little bit of a dipole moment. So you have something that's like d dot e, and so it's basically looks like sigma plus essentially the x of the qubit and the x of and the electric field of the cavity with some prefactor. If they're not resonant, then this term sort of it doesn't conserve energy. You can conserve energy by going to second order in perturbation theory, and then you get a term that looks like this. And the prefactor now looks kind of like this, but it's not so important. It's just that you get a shift, that's this number chi, which is proportional to the number of photons. And you can see this looks like the qubit frequency, like the thing in front of the sigma z is the qubit frequency. So basically we get a shift in qubit frequency, which is proportional to the number of photons in the cavity. And so if we do spectroscopy on our qubit, so let's say it's in the ground state, if there's no photons around, you get some peak. But now if we put some photons in the cavity, you get actually this plus, let's say, so this is like we just displaced the cavity, we put a coherent state in there, and we'll get a different peak. So this is the same one, this is the ground state, but now there's also a peak for 1 and a peak for 2 and a peak for 3. And importantly, this interaction is of such high quality that these peaks are really well separated. So for example, if we look at the 1 peak, we can imagine exciting it here, and you would have a high probability of getting an excitation if it's 1 and almost nothing if it's 0. But you can also do this with 2 or 3, and we'll use that later. So we can measure whether there's any photons in the cavity by measuring our qubit. And an important thing here is that when we're measuring the qubit, not the photon. So most photon detectors or counters, right, the first thing they do is they absorb the photon and maybe turn it into an electron shower or something like that. So the photon is gone. A very key idea here is that this photon is sort of shifting the qubit, but it's not getting destroyed in this process. And so we can measure it not just once, but we're going to be able to measure it many times, and that's going to be pretty critical. Okay, so yeah.
So for the axion coupled to the photons to the qubit, you're going to do through the photons or through the I guess you couple axion to the transmon. Is there like a Hamiltonian? Is there a term you write down, because A here is your photon?
So basically an axion comes in and it scatters off of the magnetic field and the boundary conditions and becomes a photon in the cavity.
Okay, it's 1 for 1.
Let's say that's happened, and now we want to detect that photon. So all of the dark matter physics already happened, and that's where we come in with the qubits. Does that make sense?
No, this part I understand. Yes, it does. But this relies on the having external field to take care of the time reversal, right? Like, so you can convert your axion into the photon.
Yeah. So I mean, there's two ways. So it could be that this qubit that's coupled to this cavity. Qubits don't like magnetic fields. Certainly not if it's. You could put it potentially in a medium-sized magnetic field, but if it's a really big one, then you won't want it. And so you want to we would probably have a separate transduction cavity that will live in the magnetic field, and then the photon would kind of propagate over to the qubit detection cavity. I'll show you what I guess, Aaron kind of already showed you a picture of what that cavity might look like. And that's definitely one of the upcoming challenges is to get the photon from between those two things safely, but I think is doable thing. There's also these hidden photons which don't solve this QCD axion or this QCD kind of neutron dipole moment problem, but are at least not disallowed by any known physics. In which case you don't need the magnetic field. And so I'll show you some things where we've put some bounds on these hidden photons, and that's basically like an axion, but where it just spontaneously converts and it doesn't need the magnetic field. And I guess there are also plausible dark matter theories that work like that. Okay, so anyway, so we have this, and what we want to do, and we can do either, do, if we just excite it around here with a narrow bandwidth, we can tell that it has a photon, or we can do what's called a Ramsey experiment and look for the parity of the system. So the idea of that is that if if we do a pi/2 pulse and we flip it down into the axis, and then we let it process, and we let it process for a time such that if it was an even number of things, then it will come back. But if it's an odd number, it will actually flip. So we basically, if it's odd, we would get this. If it's even, it will either do nothing or it will go, n 2 pi around. So so this is kind of demonstrated here for 2 different scenarios. And so we can do it. So in the first experiment, we're going to use this technique. In the second experiment, we'll use the pulse spectroscopy technique. But either way, what you could think of it as doing is it's mapping the an extra photon onto the qubit being flipped or not. And so the idea is that if we now measure the parity, and we intentionally, in this case, we ideally put in 0 photons, and so we should get 0. And so we're measuring the parity of that cavity, and we see that it's 0, 0, 0, 0, except for this one time, and the rest of the time is 0. So I mean, I suppose it's possible that this was an axion, but it seems pretty unlikely. And this is sort of a challenge. So these measurements are happening. I wrote a number of events, but these measurements are happening every 10 microseconds or 100 microseconds. Whereas the and so if we have an error every millisecond or something like that, then and we only have a signal every 10 seconds. Every time we have a false positive, we need to measure many more backgrounds. So we have to wait for another single photon to come in, or many single photons to come in. So this is a problem. We really need to suppress this dark count. And similarly here with 1, we get it. And you can see actually there's slightly more errors with 1 because it's more chances to decay. So we need to figure out a way of getting rid of these sort of dark counts that are really coming from kind of technical aspects of measuring the qubit, not from actual background. So these aren't real background photons. These are actually just qubit measurement errors. And we want to get rid of both of these. And so the idea is to basically vote. So because it's a QND measurement, we can actually just do the same measurement over and over again. So we'll basically, instead of just, we can do this many times before a single photon would have had time to decay. And we can say, well, the simplest thing you could do would be like a majority voting. We do something a little bit more complicated. We do a Markov model, which is it captures all of the information we know at least for independent errors, and lets us kind of say with some confidence that we get So the protocol ends up being like this. So we put in some displacement. It could be a large displacement that's very easy to see, and we can then trend it down until we've made this displacement essentially 0. And then we can measure how well we measure our signal. And so if we do a different displacement, so if we make a large displacement, then you can see something like this. If it's a very tiny displacement, you see just a little bit of this extra peak here. And so we can then we measure and we basically, so this would be half a photon of noise. If we were using an amplifier, we would be here. And we inject photons at different rates. And what we can see is that for like above kind of a tenth of a photon or so, of injected coherent state, we can see it very easily, and we get a nice linear proportionality to our injected signal, and then at some point it levels off, in which case we're hitting the background. And so kind of this is now a background rate, which again, it could be axions, but of course it's not. In reality, it's some kind of we're not really thermalizing our photons as well as we would like. And so from the slope, you can kind of get the efficiency, and from the asymptote, you can get the background. And so this is about a background of 3 × 10⁻⁴ background photons, and so Aaron already told you about kind of, basically there's 2 ways you can win in terms of your time. You basically can either reduce your background, or you can increase your signal. And so this reduces the background basically from a half to 10⁻⁴. So you get a very large speed up comparatively. So this is sort of the type of speed up you would get, let's say, compared to the ADMX experiment, which is using quantum limited amplifiers now. So that's already a very big potential speed up. But as Aaron said, if we could make the signal rate bigger, that would also help, right? So that's kind of the next step. Oh yeah, so this is if we were to if this didn't have a magnetic field, so it's not an axion search. So I guess so you could call it a hidden photon search, but you could sort of say, well, we've eliminated, or we've set a background rate of of this 3 times 10⁻⁴, which if you put it into the units that are typically done for axion searches is kind of down here someplace. So it would be sensitive enough if we were actually if we hooked this up to an axion transducer. At least in this amount of time, we would have excluded stuff. It's maybe a little bit, we probably still need to get a little faster in order to get to Aaron's 10 seconds per tuning, but it's pretty close. And so just to kind of, so this is what our fridge looks like incidentally, and we have most of the stuff in here is for thermalization. But we're not doing enough. So this corresponds to a temperature of about 36 millikelvin. Our physical temperature is 8 millikelvin. So if we could actually, if we could actually get to 8 millikelvin, that would be more of a background of like 10⁻⁸ or something like that. So we get another 10⁻⁵ in terms of reducing the background. And if we could at least get to below, basically, I don't know if we need quite that much, but if we get to like even, so we either need a reduction in number of 10⁻⁵, or maybe I think even if we get to like a little, like not a very, maybe 25 millikelvin would be enough to be background limited. So we need to just get this temperature a little bit lower, or this photon number a lot lower. It's exponential because of we're in the sort of low temperature limit of the Bose-Einstein distribution. Okay, so now that was sort of basically how can we use a lot of fancy quantum mechanics to make a classical photon counter. And now the question is, can we do something where we actually, use some quantum mechanics to actually go even faster to enhance the rate of the signal. And so the idea we're going to use is this idea of stimulated emission, just like what's used in like a laser, but we're going to do it with very quantum states of light. We're going to make these Fock states. So now these are not classical states. They're not coherent states. They're actually, you really can't make it without some kind of quantum interaction. So the idea is that, so the normal thing that we're doing is we say we have vacuum. So that's just like this. And if we shift the vacuum a little bit, we'll see a little bit of one projection onto one photon. And, but this, you can see that this, not only was there uncertainty that we had from our amplifier, which we've now gotten rid of, but there's uncertainty in the state. Like the state just has some broadness to it. If we make a Fock state, on the other hand, and we plot, this is what's called the Wigner tomography, but it's basically kind of a quasi-probability distribution, and it sort of, and so you can see that we get these rings, and there's one ring basically for each photon, and so now you can imagine that if we displace it, so what the Axion is doing is displacing a little bit. So if we shift it a little bit, we're going to be much more sensitive, because we're going from sort of 1 to 0, or something like that, over the scale of this radius. Whereas here we're going on a much faster. We have these sharper fringes. So that's one way of thinking about it in terms of this like kind of the, this kind of Wigner space. The other way of thinking about it, if you like algebra better, you can think of it like this, where if we take the projection of this displacement, which is our Axion kind of displacement, we basically, because we have this n to n+1, we actually end up with an n+1 enhancement. And so what we're going to end up detecting here, we're going to detect in the number basis. So we prepare this state. So we have to do a bunch of quantum stuff to prepare this, let's say, well, we're not even going to get up to n=10, but we'll, some particular Fock state. And then we will look for the n+1 state. And if we see n+1, then we will, assume that must have come from either an axion or, of course, some thermal photon or something. So the way we do this is we have this Hamiltonian, and we did it in this particular, another type of cavity, but same deal. And we're going to do what's called quantum optimal control. So there's proofs that this Hamiltonian is universal, and you can actually create any state you want. In practice, what we do is we just let machine learning figure out how to do it. And so this is an evolution. So what we do is we play this pulse, and each of these is a snapshot of this tomography. And this is making us a 1 photon state. And we can make and so these are all states. This is actually data. This is not simulation. So this is vacuum. This is 1 photon, 2 photons, 3 photons, and 4 photons. So so we can make these states, and then we can characterize them either fully with tomography, or we can just do kind of a spectroscopy there. And so what we're going to do is we're going to, let's say, make, I don't know, let's say the 2 state, right? And then we're going to probe on the 3 state. And if we made 2, and we're going to then check that it was really 2 first. And then if it is 2, then we'll look for 3. And if we see 3, we'll count that as an extra photon. And we're going to look at this kind of efficiency curve again versus the number. And we'll do it. And yeah, and we're going to do this because this is many measurements, and it's kind of good for making these pictures and characterizing things, but it's not good for detections. Too slow. So we're just gonna. So what we do is we basically we're going to do our optimal control, and then we're going to first do a couple detection pulses, a couple of QND detection pulses, to really make sure that there's nothing in the n+1 state. So we're going to just really make sure that it's either n, which is what we want, or if there was a mistake, at least it should decay down, in which case we'll lose efficiency, but we won't get dark counts. Then we're going to do our mock injection again, and then we're going to do our detection the same way. And so, and so now what we do is, so we can repeat the first experiment again, which is just 0 to 1. So that's exactly what we did before, more or less, except with the different, instead of parity, we're using this high pulse detection, and that's fine. And then here we do the we put 1 photon in, and we put in 2 photons, and then 3 photons, or 2 photons, and then 4 photons. The 3 photon actually was screwed up for some technical reason, but and so basically, if we put in these photons, you can see that the slope is higher as we go up, and we can actually get more a higher signal rate. And so you've probably seen these like LIGO plots where you have like kind of the standard efficiency, and then you add squeezing to that or something. So this is kind of, this blue region is sort of how much improvement you get from the stimulated emission, and it's roughly a factor of 2 or something like that in real terms. But it really would be like your signal rate, the rate at which you scan, would go 2 times faster if you do this. And it's kind of it's almost software for this sort of approach. So we can sort of get this going, and then hopefully add this later as almost as something close to a software upgrade. So this was our first one, and then now if you add in this stimulated emission, we can also add another point on the curve. And then finally, I'll just flash this quickly, but we need a cavity to work in a magnetic field. And so normally we like superconducting cavities, but we can't do that. So we're going to use a copper cavity, but copper is not that great. So what we would like to do is prevent most of the field from getting to the copper. So we're going to sort of reflect it back with periodic sapphire shells. And so you can sort of see what the kind of decay is, and it's exponential in the number of layers. And even putting 3 or 4 layers makes a big difference. And so here's an example of it. So I think Aaron already showed you this picture, and this is what it kind of looks like inside. And then that gets already to about a Q of a billion, limited primarily by kind of actually misalignments and things like that. So this is good enough that the axion line with itself is only supposed to be about 1 million. So you're getting most. It's always better to have higher Q, but you're getting most of the benefit. And so the idea would be that we'd have to get. So we have this cavity now. We need to make it tunable. Well, here. So on the outlook. So basically, we've got our counter here. There's other. I think there's other groups also trying to make photon counters, and there may be other simpler ways of doing this, or more featureful ways. So I think there's definitely still room to innovate on this, but it's already pretty good. Basically, if we could just get the thermal background down, which is probably not due to this internally, but is probably due to other stuff. But if we could get that down to the temperature of the fridge, it would already be sensitive enough. We could get the background to so that we're, there's essentially no background photons in a typical signal period. And then we have this cavity that works, but we need to be able to tune it somehow. So we need to be able to have a tuning rod, and it has to be stable enough to not shake the cavity frequency around a lot, and also to not heat up the cavity. We have to thermalize this very well. And then we need to get the photon from this cavity into our transmon cavity. So we have all these things, and if we can do all that, I think we can actually just start skinning for these axions. So I think we're pretty close, and at least on this side we're actually in pretty good shape. With that, I think this is there's a real gain from using these qubits. It's not just using them would actually just make the thing go faster. We can get even a little bit more by using the stimulated emission trick. We have cavities that can tolerate the field, so that's we can do it. And so I think we can speed this up, a factor of 10,000 times or something like that, compared to the rate that if you were to just continue this like ADMX kind of scanning, which is great, of course, but it makes it sort of just barely possible to get maybe through. And I think this technique would probably go through about 30 gigahertz or so, maybe a little higher depending on some other details. So with that, I'll just thank everybody that we've worked with.
All right, thanks so much, Dave. So questions? Okay, maybe I'll start. So yeah, I mean, the scheme of using the Fock states for detection, I've never heard about this. I mean, sounds really cool. Question is, like, is that the optimal one? So to go to the number states, or there's some other fancy states that one cook up with?
So Aaron and I have discussed this. So I think Fox, I don't think there are, I think several choices that are probably pretty comparable. So I think a Fox state is, I think, pretty optimal if you don't know what the phase is. You could also use like, I think a four-legged cat also, I think is roughly the same sensitivity. So if for whatever reason it was easier for you to make a cat state, you could do that. I think also a GKP state is also sort of equivalently sensitive. So I think all of these are I think you can kind of saturate the Heisenberg bound with all of these. They're pretty close. So there might be small factors, and of course there might be practical reasons why it's easier to do one versus the other. Basically, you want something that's all fringes. Like Vladimir Vuletic gave a seminar here recently, and where he basically found that actually with spin squeezing, like you can do anything that kind of scrambles also, right? Like because if you make a Wigner tomogram that's just kind of randomish, it will have a lot of structure. Basically, anything with a lot of structure, will have very small overlap to if you have small displacement, you get a big change. So so actually, it's not that you have to do any particular one. We like the Fock state just because it's relatively easy to prepare and it's very easy to detect. Like if you're, like we can sort of do this kind of post selection to make sure that we really got the state, sort of say like we prepare 5 and let's really make sure 6 is not occupied before we start measuring. Right.
And it's really just the effect that the fringes are getting closer as you go to higher fringes, right?
Yeah.
So that's how. Yeah.
Exactly.
Okay. Okay. Other questions?
I have a question.
Yeah, please, Sasha.
So maybe we can do it in the discussion session. I know you kind of bounced it off by saying that you already have an incoming photon is produced, but in terms of the conversion and the efficiency of the axion into photons, there's a particular 1 versus 2 or the symmetry restrictions. Do you have any comments on that? Because toward the end of it, you had the slide where you had the separate cavity to produce, again, the state swap or whatever you call it.
Mm-hmm.
Can you elaborate on this guy? What are the symmetry restrictions? Do you need to pretty much any cavity would do any kind of magnetic field would do? What are the
so there's kind of like
bottlenecks?
Form factor, and so you want like there's a you want like basically it's like the integral of like E dot B or something like that. That says like kind of effectively like what fraction of the volume of the cavity is being used to do the conversion. And so yeah, which is a shame because right, like it would of course be nice if you could have you like
Yeah,
right like
basically
make
for the single
multi-moded
mode,
cavities that are bigger, for example, or things like that. But if you know if the electric field is oscillating back and forth, then it partially cancels out and stuff like that. So there are you know Aaron has had a bunch of clever ideas about you could make funny slow wave structures that are multi-moded that might allow you to actually kind of get around some of these things, or with dielectrics you can also kind of create imbalances. But yeah, so there definitely is an issue about right, because like the thing you would really like to do would be like, right, if I would like to take like the big like ADMX can and use that at 10 gigahertz. Like it has modes at 10 gigahertz. If I could get that volume, it would be great. But the problem is that those those are basically the sign of the field is changing every kind of node, and therefore mostly canceling out. So, but there are people who are thinking about, like, again, there are schemes like if you could, for example, make it so that maybe it mostly cancels out, but but it's imbalanced by 30%, then maybe you take a 1/3 hit, but you get to use a much bigger cavity. So I mean, I think there definitely is a line of research there that does it. I mean, I think that's also probably a thing with bread, right? So like the bread flavor of stuff is basically using a surface to do the conversion. And so there's again a surface area to volume issue. So even though it's better in a certain sense than having just one little tiny lambda cube cavity, there's still kind of a surface to volume like factor that we're losing. And so I think it does feel like solving that issue would be a big way of enhancing the signal rate. I mean, and there are attempts like, so Shaolin Kuo here is trying to make this sort of conical cavity. So the idea is that you sort of have a quarter, a half wavelength between two conical shells, and then you can tune it by moving, and they all move together. And so if you could have sufficiently precise tolerances, you could have a potentially many cubic wavelength volume thing, and get around that. And so that would be another way where you could potentially increase the signal rate by very large factors. I mean, kind of the volume of your magnet divided by the lambda cubed kind of scale things, or in the bread case divided by, I guess you get 1 lambda there, and in the cavity case you get the ratio of the volumes.
Yeah, I can mention that the equivalent consideration, if you wanted to use some kind of material with a tunable resonance, is that you really have to maintain a uniform band gap. So if you had like 100 little tiles of sample materials, you'd have to make sure the band gap was the same in all 100 of them to within like 10% or 1% or something, in order so that the phases of the photon wave emerging would add coherently.
Yeah.
It's interesting. You guys are basically mostly, this latter part is mostly gearing toward the photon-based detection. Which is interesting, yeah.
Yeah, or similarly, if you wanted to absorb directly onto the resonances, as what Catherine was saying, and she was talking about like a kilogram of material, you really have to make sure also that the band gap of the receiving mode is again the same, and it's not that the band gap wanders around all over the place depending on where you are in the material.
All right, any other questions? So if not, thanks Dave again for a wonderful presentation. And our final presenter is Sasha Blatsky. So last but not least, as they say.
Okay, I'm allowed to share.
You should be, yes.
Should be. Okay, let's see. Okay, you see my slides?
Yes, we see the slides. Yeah, so the title is Axion Coupling in Multiferroic Sensors.
Okay. Okay, so I'll talk about the sort of drastically different take on the how to probably couple to axion, but I think actually there is also might be interesting condensed matter conversation about the multiferroics hosting effectively axion excitations inside. So this is work done with a number of collaborators, and there was a couple of papers out, one preprint more recently, and we will lay out the idea. So we are relatively newcomers to this field, and if I ask a lot of questions, I hope you take it in the right way, because we're trying to understand what the bottlenecks are. So the story is obviously about axion and detection, and I want to bring to the conversation this idea of the multiferroic as one example of multiple ferroic order material that might be a natural sensor for the axion without any external field applied. Okay, so the idea is actually what is multiferroic. Multi means many, ferroic means ferro, and so it means basically the material with the orders more than one ferroic order. So typically people look at the ferroelectric and the ferromagnet. Later on, actually, people started broadening the classification, allowing for some spiral and longer range and modulation of magnetic order. But for the sake of this conversation, it's going to be ferroelectric, ferromagnet. So there is a material out there where actually you grow it, you cool it down, and it basically spontaneously forms ferroelectric and ferromagnetic order on its own with no field applied. Obviously, training would be involved if you want to have large domains, but basically spontaneous symmetry breaking takes care of the formation of this order. So the background on the axions I probably should not cover here. That's been exhaustively covered by previous speakers. I should point out that there is a couple of couplings people discuss in this context. One of them is essentially the coupling of E dot B. That's a coupling with gamma A between the axion. In my case, it's noted A, and then sometimes it will be called theta, and the pseudoscalar quantity, right? So the A is a pseudoscalar, it's bosonic, we believe, and is coupled to in the presence of electric and magnetic field, it's coupled to this two-photon process. There are other terms that coming up from this high energy expansion that comes down to essentially Dirac fermion interacting by the fifth current to the gradient of the axion field, right? That's a term that Catherine mentioned as a gradient of A coupled to the spin, if you do the non-relativistic expansion of the Dirac spinner. And so that's the one we found a way of actually how to convert this into something that looks like this, but for multiferroic. Okay, so there is this linear coupling that I want to apply to my condensed matter quantum system. Okay, so as I said, multiferroics exist. There is a whole set of them. They do show very interesting interplay between electricity and magnetism, that you can manipulate magnetic order, for instance, by controlling the P, or the other way around. And what's interesting in the context motivated by this either decoupling, there are materials which develop spontaneously on its own, develop n parallel to P. So equivalent to what we've heard so far is actually you have a cavity where at the same time you have electric and magnetic field, and it basically permeates the whole cavity. And you have basically collinear M and P. All right, so the examples of this I'll show down below. All right, so what's the motivation? Motivation is, can we use multiferroics then as the axion detector? So I'm just looking at this axion coupling to electric and magnetic field, and for me, the M and P are stand-in for the E and B. So the hypothesis is there is a M dot P coupling, and indeed there is one, but it's coming from this coupling to the matter field, not to the photons. So you need to work on the Dirac expansion of this equation. Okay, so ingredients for this is that I need to have a linear multiferroic, namely linear magnetoelectric coupling, namely electric and magnetic field, or ferroelectric vector and magnetic vector coupled linearly. And obviously, as anything in this axion field, the detection is tiny. So I mean, I have to have a very sensitive magnetometer. So for me, the choice would be look at the large area squid. Okay, so advantages are one that it's already been again discussed. What we see is an interesting convergence between the downward push for the axion mass, where people start looking at lower excitations and threshold detections actually for the lighter and lighter axion mass. And eventually this comes into realm of the quantum materials, where collective excitations and wave-like, not particle, not scintillator, but wave-like excitations and wave-like detection becomes viable. And what I mean by that, actually, there is a kind of story about absorption, right? And I'm talking about essentially collective mode excitation instead of just kind of, so it's absorption in a way, but I'm not looking at the speckle on the photographic plate. I'm not looking at the bubble forming in the bubble chamber. I'm looking at the effectively collective mode launched in my quantum material. Okay, example of this material where this parallel M and P spontaneously occurs is lutetium ferrite oxide, and there is, I think, scandium doped in for whatever reasons, but basically we do have the situation where first, as you call this material, we have charge order sets in at much higher temperature, and then as we cooling down, eventually we get to the magnetic order. So this is about 1200 Kelvin, and this is about 160 Kelvin, whatever. Yeah, this is 120 Kelvin, you know what I mean. This is 1200 Kelvin, this is about 160 Kelvin. All right, so how do you do it? I will use this Ginzburg-Landau approach just to illustrate the point. We don't need to go through the equation, sorry about the equation, but basically you have a free energy describing magnetic degrees of freedom, you have a free energy describing ferroelectric degrees of freedom, because it's multiferroic, and they have a coupling. You can have a tensorial coupling. I'm very more interested in coupling between P dot M, and this theta is this term that I was telling you that actually you can work out, it appears. And so the assumption is that when axion flies into this material, it just kind of suddenly realize that it lives in the soup of other axions. So yeah, like it's they actually have their own origin because of M dot P coupling, and then the possibility is actually maybe you can have a crosstalk between this incoming axion and collective modes in this material. And I will tell you about the strength of the effect, which is very small, and the possible readout with detecting magnetic field fluctuations. Okay. So a couple of things. So how we arrive at this is that you look at this coupling, and in the there's a fifth current coupled to the gradient of mu, gradient of gauge potential. I mean the gradient of A field. There is a term that looks like a gradient A dot sigma. That's been discussed so far. And usually, what's happening in the kind of high energy and field theory community, right? If you look at the long wavelength fields, the gradient has to come from A. Right, so, but now if I have the state psi, like I have a complicated state, I have like a band structure, I have the states, so I have electrons of different orbitals, right? So this psi is no longer just Dirac relativistic fermions, it has a band index, it has different symmetries. So I should probably sandwich this one with respect to psi, and what will happen actually, the trick I will do, I will flip the gradient and apply the gradient to psi. Now, so then if there is a net expectation value for this operator, sigma dot gradient, then I have a finite value like everywhere per unit cell. There's a price to pay, of course. So the idea is that, and I will explain in a second, but the idea is that you have an axion field coming in, and if I have within the unit cell ferroelectric moment, so my P ferroelectric polarization is coming psi, grad psi is finite, and expectation value of sigma is finite. I can have an effect. But the price to pay because of this gradient or because of the high order expansion, there is like extra one mass electron. So it's axion over the electron mass, small compared to others, compared to this direct photon coupling, two photon couplings. Okay. So again, just as well, because it took, we've been discussing it for quite a bit with Frank Wilczek for this axion, whatever we had some working group, and I was listening to a lot of this. Once we got the idea, it took a while for us to make the point. So with respect, I will just kind of drill it down a little bit more. Okay, so the idea is actually there is a difference, obviously, in terms of what we're looking at in the quantum materials versus quantum field theory. In the quantum field theory, when you have the gradient A dot sigma term and expectation value, you have a single psi, right? You have a single wave function. And so that's what I was saying, that the only place where the gradient can come from is some wave vector of this psi, for instance. Technically, it's not true for the crystals, for solids, because each unit cell, say has, for instance, have orbits of different parity. So this expectation value of psi, grad psi, can be finite for extremely localized wave functions within a unit cell. This is no longer Q equals 0 conversation in the field theory. This is actually atomic sized wave functions. But as long as I have, for instance, S and P orbitals in this psi, I have a finite expectation value for that. Equivalently, it means if I have a polar crystal with a broken inversion within the unit cell, this expectation value is finite. And so example here, you take a, and by the way, this is always true that for any of these ferroelectric orders, you need to have more than one orbital. So inherently, one cannot have this conversation on a single type of wave function. You have to have wave functions of different parities be present to develop the finite ferroelectric order. And so then the same goes for sigma. So, but if you have a sigma spin polarized like a ferromagnet, then sigma comes out to be expectation value, and then you have a sigma, essentially m dot p. That's the origin of this term. Right, so the idea is actually, I'm not looking at long wavelength expansion. I'm looking at just basically applying the wave function as they come in the 1 year in the block representation. And I'm just doing the sandwich for the Dirac expanded Hamiltonian. And I'm getting the term that looks like p dot m dot proper coefficients dot a. Now, so what it means is that if I have material that has a scalinear ferroelectric order, I have a coupling between the theta, this electron or my axion field, and p dot m term. How much? Of course, it will be tiny. So running ahead, if you estimate the values, we get about 1 attotesla fields for typical fields. And this is for the domain size of about, I forgot, maybe 1 centimeter domain size for the ferroelectric moment. And the magnitude of fluctuation magnetization we can produce is attotesla, assuming particle coupling here, which we estimated. So next, I will just, so my coupling is the same as the 2-photon coupling. Instead, my lines are now P and M coming in and creating A, or the other way around, A coming in, creating P and M. And then, of course, I will assume that I have an A field oscillating with the mass, typical mass of axion, and the kinetic energy of this A field is about 300 megavolts per cubic centimeter, as estimated, like from QCD or light axions. Okay, material candidate is here. It's a ferroelectric at about 1200 Kelvin, and then at about, so what the story here is that for you have lutetium, yellow, whatever, yellow sphere, the lutetium, red ones are iron. So technically it's made of a stack of these layers of these triangle or interleaved, basically triangle layers of the iron, and they are like at 120 degrees laying in plane. So below 1200 Kelvin, actually, as you cool down, you have a ferroelectric order, and technically it's in antiferromagnetic state. There is no ferromagnetic moment coming in. And then at 160 Kelvin, the lattice distortion comes in, and some of this octahedral tilt. And because of that, this ferroelectric, the magnetic moment requires a finite value out of plane, and it becomes ferromagnetic. So the tiny canted value of the ferromagnetic moment out of the plane, that's basically generates my P dot M. I should say that we just took one as existence proof. By far, it's not optimized for detection. Right? But basically, technically, there are materials out there. I'm sure there are more. And in fact, actually, there are other reasons why it's not the best material. But there are, as a matter of principle, there are materials which have the kind of parallel or collinear ferromagnetic and ferroelectric orders. Okay, and then the logic is the following. I have two ferroic orders. I'm coming down. Say if so it happened that if a charge order happens first, so in this space, say I'm way below 1000 Kelvin, then actually my ferroelectric order is fixed as nail. So within the same domain, P is the expectation value of P is finite. Right? And so it means that I can have a jitter in theta in my axion field producing jitter in M, because P has a finite expectation value here. Right? And so the idea then is, because this theta is a small oscillations compared to whatever underlying energy scales are for M, these tiny oscillations of the coupling and modulations of M should be felt. And so the best way to do it would be at the critical point where the magnetic order barely sets in. So you want to be sitting here. And so I should point out the fact that P is actually finite everywhere. This means that you have a spontaneous symmetry breaking where without any applied external field, you have a capacitor giving you per unit cell giving a steady value of the electric field that's required for your what would be the two-photon conversion. And then I will do the one-for-one. I will do excitations of theta translated excitation of M at the soft spot where M itself is soft. So we use the classical equations of motion. You have an equation of motion with some damping coefficient, with the stiffness term, inertia term. This is a mass term, depending on the above or below magnetic order. And then the theta terms, just like in the standard mixed electrodynamics of the axion, mixes up electric and magnetic field, so it mixes up P and M. But now the P is fixed, so the place where we actually are the most interested is the theta works as a source term to excite M oscillations. So you work out the math and you get this linear term in theta. So you have a modulation of M linear in the axion coupling that obviously knows about how close you are to transition temperature. And basically, like I said, it's linear in theta and depends on the strength overall of magnetic electric coupling. Now, because theta is small, effect will be tiny, so there is like pretty serious constraints on whether it can be done or not. So I believe now, even though we made a proposal for the current material, it's not possible. So just to give you the estimate on this color plot, if you look at the theta to be, say, on the scale of 10 to minus 15, and if you look at delta t, so what's here? This is a logarithmic plot, logarithmic scale for the how close you are to transition temperature, say 10 to minus 3, and you have a 10 to minus 15 from this color plot, you can see that you're roughly at the green area. So your log M modulation is about 10 to minus 7, 10 to minus 6. Okay. And so this produces a very small oscillation. There is additional constraint on this. The fact that this oscillating field should be felt as a adiabatic field means, okay, so there's a more, okay, so when you go through magnetic transition, right, you have a critical slowdown for the magnetic degrees of freedom because you basically the stiffness for the magnetization can go down. So your magnetic order start getting very wobbly, very slow. And then you're agitating with the axion time, which is inverse of the frequency of axion, depending on what frequency you're at. And so you want to be at the regime where axion time, right? Axion time is, let's see, axion time is longer than the typical oscillation. So you have a net effect, actually, like a DC field effect. So you're in this regime and the adiabatic regime, the axion time is longer than the magnetic time. And so in this case, you want to be outside of this critical region. But then actually, if you go to higher temperature, your coherence times for magnetic excitation die out, and then you have a cryogenic actually questions about how far you can go into low temperature. So overall, we estimated roughly the effect is on the scale of 10 to minus 8. And then we estimate how much of a bump, how much of the extra magnetic moment you can produce in these oscillations. Okay, so in the interest of time, let me just show you the launching magnetic wave. So this linear term in theta works out that you park yourself very close to transition temperature of a magnetism. So you're nominally in paramagnetic phase, but then oscillation theta dips you down because you see it actually comes with negative terms. The bracket can be made negative if you dial it right. And so what it means is actually you're effectively modulating magnetic temperature. And so if the axion arrives here, for instance, it can launch magnetic waves through the sample. And if you put some magnetic detector on the surface of the sample, you might see magnetization. So that's actually the dynamic detection. And then, can play with whether we do the purely harmonic, a steady incoming CW kind of axion CW field, or you can do the pulse. You can see different ways of ringing of magnetic excitation in this multiferroid. Now, I just want to finish also by saying that later on we had to write our own comment on our own paper with Benjo, where we were saying that it's all fine, but if you take a realistic size of the sample, say if you take in this color plot, if you look at the domain size of about 10 centimeters to 1 meter sample, and then you look at the temperatures, realistically, it can be at this lutetium-based material, say you can be 1/10 below TC, you barely get signal to noise, maybe like, so certainly you never reach out to 1, or you never reach to a comfortable value where you can have a lot of signal. So it's not to say that the idea is bad, it's just to say that the material has not been optimized. But from what I hear about the magnets costing $250 million, maybe some of the proper design material might be, quantum material would be useful. So I'm just saying you should be dealing with the baby steps compared to the maturity of conversation and what's happened in cavities and other places. But I think quantum materials overall offer a very interesting alternative pathway. And again, the advantage here, so let me see if I have it in conclusion. Yeah, so advantage here is that for this particularly sort of tuned or designed quantum material, what we have is actually we have a matching of scale, which is happening. But yeah, we don't have a tunability of 9 orders of magnitude that Aaron was saying. It happened to be like a sample for sample or material for material. So that's it. But then what we have is actually we have a whole bunch of unit cells that work in synchrony. Right, so it's a product state. Each of the unit cell essentially looks like the macroscopic condensed state. It's like a product which each of them has the same P and the same M. So I have a Avogadro scaling of unit cells given to me by nature. I do not need to have the external fields applied to generate this P and M and look at the equivalent of this two-photon conversion in the quantum material. Right, and this is actually purely spontaneous symmetry breaking as opposed to other. So because everybody has the names on this thing, we just come up with mermaid multiferroic matter axion detector. And I will just finish here saying that multiferroics offer interesting alternative to axion sensing. It basically utilizes Avogadro scaling. It has a broken PNT without external fields, so it just relies on spontaneous symmetry breaking, macroscopic single domain symmetry breaking. It does lead to the linear polarization of the axion field to this pseudoscalar product, and it's a macroscopic coherent effect. The source of noise damping systematic material search for the material for optimization would need to be done. So I'll stop here and take questions or whatever we want to do it.
Yeah, wonderful. Thank you, Sasha. Questions? Yes, Peter.
Yeah, I have a quick question. So when you say systematic material search, what is kind of one of the most important things? Do you want to have like a larger projection of M1 to P, or is it more like domain sizes or temperature?
It's basically the main size. The main size basically gives you logarithmic, sorry, gives you exponentially like larger value. But the other piece, I kind of skipped over. Let me see this relaxation times. Yeah, this one. So what happens is that we looked at the realistic parameters for the line for T1 broadening for the line widths for the lutetium. So technically, the best place to be for this thing is that you have essentially quantum critical point. You barely go magnetic near T equals 0, because then actually your magnetic relaxation times are much better from the beginning, right off the bat. You don't need to do anything because basically it's very low temperatures. So therefore line widths are much sharper. So this happened to be 160 Kelvin. Without any tuning, this material has grown, has a magnetic order sets of 160 Kelvin. And so when we kind of wrote the first paper, we were excited, but then Henrik, who is the lead author, Henrik Reusing, being very careful, he looked at the numbers. He said, it's not going to work for the currently available sample sizes and the scale. So just to recap, it's about 1 attotesla for the sample size of 1 centimeter. And so, and this is for this lutetium ferrite, which we looked at about 100 Kelvin transition temperature. So if you lower it down, you can get away with a smaller sample. And this plot will tell you where we
I see. So you want to suppress the magnetic transition temperature to as close to 0 as
yes, to
possible.
sharpen up the lines, to increase this response of magnetic one to the drive. So my magnetic degree freedom will respond to axion, because axion through m.p with a fixed p is essentially pump of magnetic fluctuations.
Right.
But this thing actually, what compared to Aaron and to David's conversation, there is no photon. It's all intramatter collective excitation. So I mean, there's always a photon somewhere inside, but I'm saying actually you don't need to rely on the cavities that is externally capped and control magnetic and electric field. So your difficulties are squeezed into a different place. So like I said, you can view it as you have a 10 to 6 shitty samples, shitty sensors, right? So basically, but nevertheless, it could be actually the place to go.
Right. Okay. Thank you.
Not 10 to 6, 10 to 20, whatever, Avogadro number.
Right.
Other questions?
Hi, I have a question about the magnons. You said that the near the TC of the magnetic transition, I guess, there's already a one polarization kind of vector, and the axions will launch magnons once it hits the sun. To the launch magnet, does it need to be align with the frequency of the intrinsic magnet of the material itself due to the exchange couplings, or it can be any frequency because it's near the.
Yes. So you got muted. So
sorry. Yeah, the question is over. Does it need to be like as a specific? Does it limit
so
the
this is not
frequency
the
of theta?
There is a frequency tunability in terms of like, because magnetic degree of freedom has its own susceptibility, it's better to be on resonance. But technically you can be off resonance. It's not tethered to resonance. Because what happened, think about this. Imagine you have a time-dependent Ginzburg lambda with relaxation dynamic of M. And you're coming in and you're coming with this term here. I don't know if you see it, theta p dot m. Because p has a finite value. It's a nail down. It basically got ordered at a much higher temperature. By the time you arrive at magnetic order, this is just a constant. You can view it as renormalization of chi. So you have a 1-for-1 excitation of theta translating into M. And then depending on what the true dynamic of M is, you can choose the detection. But it's resonant in a sense that if you, of course, equation the motion of M controlled by its own susceptibility, right? So it will be picked at the resonant frequency of the magnon. And this frequency of the magnon excitations is controlled by mass term, how close you are to TC or how close you are to critical point. But technically, you can be off resonance.
I see.
So in fact, this argument. Sorry.
Yes. So the such a response will be enhanced in the magnons, like in the magnon frequency of the material.
Yes, it will definitely be enhanced. Yeah, here you can see it. So actually, you have omega axion minus omega m. So here we have a native, say, an equivalent to what was discussed. If you have a native cavity or native mode frequency for the magnon, then when you sweep omega through this, you'll get resonant enhancement.
Okay.
And so yeah,
go ahead.
I just was going to show that here's a bump. How much of the magnetic enhancement you can get 100 millikelvin, but if you go to 1 microkelvin, you get much better signal. But then, like I said, this is a heroic effort, right? It's not going to happen. So this is just to show that going to lower temperature space.
Got it. Thank you.
So the damping presumably also depends on temperature, right? So I suppose near Néel temperature should be probably higher than at low temperature.
Yes. Yeah. So there is no miracle here. We just took the what's known about the, I forgot, ESR or some not ESR, some magnetic lines on the lutetium, right? So there is a certain gamma. But then, of course, basically, depending on the engineer, you can make it material softer. So definitely, I remember from this, going to smaller omega m helps. And for 2 reasons. One is that you have a less of a noise in the environment, and the overall magnitude of your polarization can enhance. But there might be some other reasons actually why you might not go completely to very low temperatures.
And is there a benefit to doing it sort of the other way around, where magnetic temperature is above the ferroelectric temperature?
would be great if you can find the material. Yeah, I'm sure you can probably do something with the ferroelectric, but usually what happened in the ferroelectric community and all this multiferroid community, they are pretty much in the same kind of like a engineer a lot of this responsive with impurities. So they can drop down magnetic temperature by doping it with something, but then actually the price to pay, everything gets very disordered.
So typically ferroelectric temperature is much higher than magnetic one, right?
Yeah, typically that's true, because the ferroelectric is controlled by Coulomb, whereas magnetic is controlled by some version of magnetic exchange or interaction.
Yeah. Right, but I guess like I mean, so address Aaron's question. So he needs big magnetic fields, right? So here using magnetization, you probably can get like to a few Tesla, but it's not going to be anything like particularly astronomical.
No, in fact, I want to be with no magnetic field, so I can see something compared to nothing.
Yeah,
so
no, exactly.
But
you're using magnetization essentially as a magnetic field, right? So I can convert it into
as a sensor.
Yeah. Right.
So my point actually, what I do is actually I use ferroelectricity as a way of doing in the Aarons or whoever is doing multimode cavity. I fix E, so I don't have to worry about it. Somebody was mentioning, David was mentioning the integral should be finite across the whole cavity. So my E is present everywhere, and at the same time M is present. So M dot E is your figure of merit E dot B for the cavity. It's working as a scaling with the sample size or with the domain size. But detection is going to be that I have no magnetic moment and introduce magnetic moment. In fact, you can show that for DC version of the detection, I commented out the same. Just like you have a mode coupling, right? So basically, you have some modes like, so here's the dashed red and dashed green line. So you have some ferroelectric and magnetic mode. So ferroelectric is already masked out because basically it's ordered. But then turning on this coupling to Axion induces extra level splitting. So some levels get pushed up, some levels get pushed down. So if you're right on TC, you can detect, you can form the ferromagnetic state. Right? So basically modulating TC, albeit you're modulating this frequency of this theta field, but you're basically driving the whole sample into ferromagnetic state. So if the wavelength of your axion is actually covering the whole sample start behaving weirdly, so going in and out of the magnetic state.
Right. But I mean, so there got to be some sort of heating sort of coinciding with that, right? And you have to like get rid of the heat. So
you mean
I guess heating is cooling.
Heating is what?
Heating is
because
easy.
of what?
I don't know. Because of your Axions, I suppose.
Well, if the heating is because of Axions, congratulations, we made an engine.
Right. I mean, but like in the ideal case, of course, in reality, there will be many more things going on.
Yeah.
Anyway, so any other questions to Sasha specifically?
Need to read the paper.
Yes.
Hi, Sasha. I have a question about the Magnon. So
paper. Just one sec. Plug, shameless plug. So basically, there are two things. One is there is the original paper, and there is, like I said, it's a funny thing. We write a comment on our own paper because basically we're saying that it's not like technically anything is wrong in the calculation, but just we're saying actually it means that there are the materials restrictions which are more stringent. Sorry. Yeah. Question?
So
yeah, I have a question about the Magnon. So the slide you had before has like a delta M or something over theta magnetic response, that slide.
This one?
Yeah. I not know that. Can you show the overview again?
This one?
Yeah, this one. Yeah. So this delta M is due to the Magnon or?
No, this is delta M due to theta.
Due to theta.
So what's happening is this. I have a theta P dot M. I write equation of motion for P and M. I'm ignoring any oscillation fluctuations in P. And I'm looking for how much of theta fluctuation is external. It's essentially parametrically driven oscillator. How much theta fluctuation induces M fluctuation.
Theta fluctuation induces M fluctuation. But
So
there
let me
was
just
some
go back.
comment about the magnon, right?
Okay,
Like
so
it's enhanced at the magnon or something like that.
So M is
yes,
the magnet, right?
yes, M is a magnon, M is magnetic order.
But,
So I have M
what
and P.
what I'm a bit confused about is I thought the magnon, in the magnon, the magnitude of the magnetization is not really changing, it's only processing. Is that correct?
No, this is actually that's true, but if you do coarse graining, if you look at the like a 10 unit cells or something, so magnetic moments basically what's happening is that per unit cell, this is a coarse grain, this is effectively order parameter per unit volume. So what's happening is actually ferromagnetic order happens when this disorder spins, they suddenly actually start growing finite value along certain direction. And that's actually M. This is my order parameter M, right? So they can be finite magnitude, but they're totally disordered and disoriented in the paramagnetic phase, and then they develop a finite value. So I'm talking about how much of the net bulk Q equals 0 polarization develops as a result of elimination by theta.
It's just like longitudinal magnon, right? Not the transverse.
Yeah, so it's not the precession, it's just the magnitude of the polarized vector. And
Oh,
so
it's like the
because
amplitude mode? Are you talking about
Yes.
amplitude mode? Oh, okay. Like the Higgs mode.
Yeah, it is Higgs mode, exactly.
Oh, okay. Then it's okay. I see. Generally, I wouldn't call it a magnet. Okay, I see what you mean. Okay. Yeah.
It's a spin, whatever it is. It's basically ferromagnetic order. So, and the Higgs mass is this one, T minus Tm. It's exactly Higgs mode. It's how much of
Right. Okay, I see. It's not the
So
it's the amplitude down, not the phasor. Okay, I see what you mean. Yeah. Okay. Yeah. Thank you.
So I'm sorry I missed it. I'm sure people talk about somebody who gave an overview, like Peter. Basically, the very same crosstalk between E and B happened in this axion electrodynamics and multiferroics. You have a theta crosstalking forces crosstalk between P and M and the proper equations. And so that's basically cross coupling. So P, if it's fixed, isn't doing anything in this chi theta term times P. If you move it to the right hand side, becomes a source term for your agitator for M for magnetization.
So any other questions to Sasha? Or should we switch over into the discussion? We probably shouldn't have like long discussion, but maybe like, depending on the interest, 10, 15 minutes.